Cosmic Catastrophe Protocol: How Galaxies Die. Part 1: The Silent Apocalypse. Your galaxy is dying, not tomorrow, not in some distant future when the stars burn out, right now, at this very moment. While you go about your day, while you sleep, while you read these words, the Milky Way is being torn apart by forces you cannot see. Invisible streams of stars are being ripped from their homes and scattered across the void. Ancient scars from cosmic collisions billions of years old still bleed through the galactic disk. And deep in the heart of our galaxy, a monster with 4 million times the mass of our Sun is slowly devouring everything within reach. This isn't science fiction. This is the reality astronomers have discovered over the past decade. Our home galaxy, the vast spiral of 400 billion stars we call the Milky Way, is not the stable, eternal structure we imagined. It's a battlefield, a graveyard, a cosmic crime scene where the evidence of ancient violence surrounds us on all sides. You live inside a galaxy that has already died dozens of times, each death left behind fragments, orphaned stars, ghostly streams of matter that orbit like memories of worlds that no longer exist. And in just 4 billion years, the Milky Way will die its final death in a collision so violent it will reshape everything you can see in the night sky. But the dying has already begun. Look up at the night sky on a clear evening. Every star you see is moving, not just drifting through space in gentle orbits, but fleeing, racing away from disaster zones, carrying the momentum of catastrophes that happened before Earth even existed. The Milky Way appears peaceful from your perspective, a soft band of light stretching across the darkness. But that tranquility is an illusion created by distance and time. The truth is far more disturbing. Your galaxy is a cannibal, a cosmic predator that has consumed dozens of smaller galaxies over billions of years, tearing them apart star by star and absorbing their remains into its own structure. Right now, as you process these words, the Milky Way is in the active process of devouring at least 5 smaller galaxies. You can see the evidence if you know where to look. Thin ribbons of stars stretch across hundreds of thousands of light years, delicate trails that mark the death throes of galaxies that wandered too close to our gravitational field. These stellar streams wrap around the Milky Way like ghostly halos, each one representing a world that no longer exists. Each one carrying billions of orphaned stars that once belonged to their own galactic communities. The most dramatic evidence of galactic cannibalism lies in something called the Gaia-Enceladus merger. 10 billion years ago, long before Earth formed, long before our Sun ignited, the Milky Way collided with a dwarf galaxy that astronomers have named after the Greek giant Enceladus. The impact was so violent it shook the entire structure of the young Milky Way, scattering billions of stars into new orbits that persist to this day. The European Space Agency's Gaia telescope revealed this ancient catastrophe by mapping the precise positions and motions of over 2 billion stars in our galaxy. When astronomers analysed this data, they noticed something strange. 30,000 stars scattered throughout the Milky Way were moving in the wrong direction. While most stars orbit the galactic centre in one direction, following the general rotation of the disk, these 30,000 rebels were moving backward, travelling in retrograde orbits that defied the galaxy's natural flow. Their colours were wrong too. Their brightness didn't match the patterns of normal Milky Way stars. And when astronomers measured their chemical compositions, they found fingerprints that could only come from somewhere else. These stars were immigrants, refugees from a galaxy that no longer exists. The researchers ran computer simulations, modelling what would happen if a dwarf galaxy crashed into the young Milky Way. The results matched the observations perfectly. 8 to 11 billion years ago, Gaia-Enceladus approached the Milky Way on a collision course. As it crossed into our galaxy's gravitational field, tidal forces began tearing it apart. Its outer stars were stripped away first, forming long streams that wrapped around the Milky Way like ribbons. Then its core collided with the Milky Way's disk, punching through in a catastrophic impact that sent shockwaves rippling through both structures. The collision didn't destroy the Milky Way, but it fundamentally changed it. The impact may have created the thick central bar that runs through our galactic core, a feature that only 2/3 of spiral galaxies possess. It definitely scattered billions of stars into the galactic halo, that vast spherical cloud of old stars that surrounds the disk, and it left behind those 30,000 retrograde stars, still orbiting in their backward paths 10 billion years later, carrying the memory of a galaxy that died before Earth was born. But Gaia-Enceladus wasn't the only victim of the Milky Way's cannibalistic appetite. Astronomers have identified the remnants of at least 6 other dwarf galaxies that our galaxy has consumed over its lifetime. Each merger left behind distinctive signatures, stellar streams, and chemical fingerprints that reveal the violent history written into the structure of our galaxy. One of these victims, a dwarf galaxy called Sagittarius, is being consumed right now, in real time. You can watch it happening if you have access to powerful enough telescopes. The Sagittarius dwarf galaxy has already collided with the Milky Way 3 times over the past 4 to 5 billion years. Each time it punched through the galactic disk, tidal forces ripped away more of its stars, spreading them across space in vast streams that now wrap around the entire galaxy. The Sagittarius dwarf is dying slowly, being pulled apart piece by piece every time it orbits through the Milky Way. Billions of years from now, it will cease to exist as a separate structure. Its stars will be scattered throughout the Milky Way's halo, indistinguishable from the billions of other captured stars that once belonged to other galaxies. Another world erased from existence, absorbed into the cosmic machine that is our galaxy. Some astronomers believe the collision with Sagittarius may have triggered the formation of our own sun. About 4.5 billion years ago, right around the time the Sagittarius dwarf made one of its passes through the galactic disk, shockwaves from the collision compressed clouds of gas and dust in the Milky Way's spiral arms. These compression waves can trigger gravitational collapse, causing gas clouds to condense into new stars. If this theory is correct, then our Sun, Earth, and everything you've ever known exists because a dwarf galaxy was being torn apart nearby. You are the child of cosmic violence. Your existence is a side effect of galactic cannibalism. The process of galactic consumption operates through tidal forces, the same fundamental physics that causes ocean tides on Earth. When a smaller galaxy approaches the Milky Way, it experiences different gravitational pulls on its near side versus its far side. The side closer to the Milky Way feels stronger gravity, while the far side feels weaker gravity. This difference in gravitational force stretches the dwarf galaxy, pulling it apart like taffy. The stretching happens slowly at first. Over hundreds of millions of years, the dwarf galaxy's outer stars are stripped away in long streams that follow orbits around the Milky Way. These streams can stretch for hundreds of thousands of light years, creating delicate traceries of stars that mark the path of the dying galaxy's orbit. As more material is stripped away, the tidal forces become stronger relative to the dwarf galaxy's remaining mass. The process accelerates. Eventually nothing remains but scattered stars and the invisible dark matter that once held the galaxy together. These stellar streams represent some of the most beautiful and haunting structures in the galaxy. When mapped with precision by telescopes like Gaia, they appear as thin ribbons of stars wrapping around the Milky Way in graceful arcs. Each stream tells a story of a galaxy that died, pulled apart by forces it couldn't resist. The streams carry names that hint at their origins. The Orphan Stream, a trail of stars with no identified parent galaxy. The GD1 Stream, a pencil-thin line of stars stretching across 60 degrees of the sky. The Heracles Stream, the remnants of a dwarf galaxy consumed over 5 billion years ago. Some of these streams are so old that they've completed multiple orbits around the Milky Way, wrapping around the galaxy several times and creating complex patterns that challenge our understanding of galactic dynamics. Others are so new that their parent galaxies are still partially intact, still fighting against tidal forces that will ultimately tear them apart completely. The discovery of these streams has revolutionized our understanding of how galaxies grow. Astronomers once believed that galaxies formed primarily through slow accumulation of gas, gradually pulling in matter from the surrounding intergalactic medium and converting it into stars. But the evidence from stellar streams reveals a different story. Galaxies grow primarily by cannibalizing other galaxies. The Milky Way didn't build itself gradually. It consumed its neighbors, absorbing their stars and dark matter into its own structure. This process of growth through cannibalism appears to be universal. Every large galaxy that astronomers have studied in detail shows evidence of merger activity. The Andromeda galaxy, our nearest large galactic neighbor, has consumed dozens of dwarf galaxies over its lifetime. Its halo is crisscrossed with stellar streams, each representing a world that no longer exists. Other giant galaxies throughout the universe show similar evidence of cannibalistic growth. But the stellar streams represent only the visible evidence of galactic cannibalism. The invisible dark matter that makes up 85% of the mass in galaxies also gets torn apart and redistributed during mergers. When a dwarf galaxy is consumed, its dark matter halo gets shredded and mixed into the Milky Way's own dark matter distribution. This process leaves behind clumps and streams of dark matter that flow through the galactic disk, completely invisible but still gravitationally active. These dark matter streams might be passing through your location right now. The Earth, the Sun, your entire solar system, could be moving through rivers of dark matter, stripped from galaxies that died billions of years ago. You cannot see these streams, they don't emit light, they don't interact with normal matter except through gravity. But they're there, flowing through the galaxy like invisible currents, carrying the dark remnants of dead worlds. Some of the stars visible in Earth's night sky are refugees from these consumed galaxies. They weren't born in the Milky Way. They formed in other galaxies, galaxies with different chemical compositions, different histories, different fates. When their home galaxies were torn apart, these stars became cosmic immigrants, absorbed into the Milky Way and forced into new orbits around a galactic core they never belonged to. You can identify these immigrant stars by their unusual orbits and strange chemical signatures. Most stars in the Milky Way's disk orbit in roughly circular paths around the galactic center, all moving in the same direction. But stars captured from dwarf galaxies often move in highly elliptical orbits, plunging from the outer halo down through the disk and back out again. Some orbit backward relative to the galaxy's rotation. Others move at steep angles to the galactic plane, travelling paths that no native Milky Way star would follow. Their chemical compositions also give them away. Stars are born with the chemical fingerprints of the gas clouds that formed them. These fingerprints record the history of stellar nucleosynthesis in their parent galaxies. Stars from dwarf galaxies often show unusual ratios of elements, patterns that don't match the chemical evolution of the Milky Way. By analysing these chemical signatures, astronomers can identify stars that came from elsewhere and sometimes even determine which dwarf galaxy they originally belonged to. The most metal-poor stars in the Milky Way, ancient suns that formed when the universe was still young and hadn't yet produced many heavy elements through stellar fusion, are almost all immigrants. They formed in the first generation of dwarf galaxies that existed shortly after the Big Bang, when the universe was only a few 100 million years old. When those primordial dwarf galaxies were consumed by the growing Milky Way, these ancient stars became part of our galaxy's halo, where they orbit to this day as relics from cosmic dawn. Some of these immigrant stars might be older than the Milky Way itself. The galaxy has existed for about 13 billion years, forming relatively early in cosmic history. But some of the stars in its halo show ages approaching 13.5 billion years, formed when the universe was barely 300 million years old. These stars predate the Milky Way as a coherent structure. They were born in earlier galaxies, primitive structures that existed before the Milky Way assembled itself through mergers. You live in a galaxy built from the corpses of hundreds of smaller galaxies. Every star in the halo came from somewhere else. They were born in other worlds, galaxies that no longer exist. The Milky Way consumed those galaxies, absorbed their matter, and erased them from existence. And now it's carrying their scattered remains through space, a cosmic graveyard masquerading as a spiral galaxy. But galactic cannibalism doesn't just consume dwarf galaxies. Sometimes larger structures get torn apart by tidal forces. The Magellanic Clouds, the two dwarf galaxies visible from Earth's southern hemisphere, are currently being consumed by the Milky Way. But they're not going quietly. As they orbit our galaxy, tidal forces are stripping away streams of gas that trail behind them like cosmic contrails. The Magellanic Stream, a river of hydrogen gas torn from the Magellanic Clouds, stretches across 200 degrees of the sky, wrapping halfway around the Milky Way. This stream contains enough gas to form 500 million stars, material that the Magellanic Clouds are losing as they orbit through the Milky Way's gravitational field. Eventually, this gas will fall into the Milky Way's disk and form new stars, converted from the raw material of dying dwarf galaxies into future generations of stellar systems. The Large Magellanic Cloud, the larger of the two dwarf galaxies, masses about 10 billion solar masses, roughly 1/10 the mass of the Milky Way. It's currently about 160,000 light-years away, orbiting at a speed that will bring it crashing through the galactic disk in about 2.5 billion years. When that happens, the collision will trigger a burst of star formation as gas clouds from both galaxies crash together and compress. But the Large Magellanic Cloud won't survive the encounter intact. Tidal forces will tear it apart, scattering its stars throughout the Milky Way and adding another victim to our galaxy's long list of consumed worlds. The small Magellanic Cloud, orbiting about 200,000 light-years away, faces a similar fate. It's already being tidally disrupted, losing gas and stars to the Magellanic Stream. In a few billion years, it too will be absorbed into the Milky Way, its identity erased as its stars merge with the larger galactic population. These consumption events represent the ongoing death of cosmic structures. Galaxies that existed for billions of years, evolving their own stellar populations and chemical compositions, are being systematically destroyed by the Milky Way's gravitational field. Their stars are scattered, their gas is stolen, their dark matter halos are shredded. Everything that made them unique gets homogenized into the larger structure of the Milky Way. From the perspective of any hypothetical civilizations that might exist in these dwarf galaxies, the consumption process would be catastrophic. Imagine watching your night sky change over millions of years as tidal forces rip your galaxy apart. Stars that once belonged to your galactic disk get scattered into new orbits. The familiar constellations change and eventually disappear. Your galaxy's spiral structure unravels, and looming ever larger in your sky, growing brighter with each passing millennium, the Milky Way appears like a cosmic predator coming to devour your world. But the cannibalism works both ways. When the Milky Way consumes a dwarf galaxy, the dwarf galaxy's gravity also affects the Milky Way. Large mergers can disturb the Milky Way's disk, creating waves and warps that ripple through the stellar population. The Gaia-Enceladus merger 10 billion years ago may have completely restructured the young Milky Way, transforming it from a simple disk galaxy into the barred spiral structure we see today. Some astronomers believe the Milky Way's disk shows evidence of ongoing disruption from these mergers. The disk isn't perfectly flat. It warps upward on one side and downward on the other, creating a gentle wave that ripples through the outer regions. This warp might be caused by the gravitational influence of the Magellanic Clouds, tugging on the disk as they orbit. Or it might be the lingering effect of past mergers, disturbances that haven't fully settled down even billions of years after the collisions that created them. The galactic disk also shows vertical waves, ripples perpendicular to the plane that cause stars to oscillate, up and down as they orbit. These waves were likely triggered by dwarf galaxies punching through the disk during merger events. When a dwarf galaxy crosses through the disk, it acts like a stone dropped into a pond, creating gravitational ripples that propagate outward through the stellar population. These ripples can persist for billions of years, a permanent scar left by long-dead galaxies. The Sun itself participates in these motions. Our solar system orbits the galactic center at about 230 kilometers per second, completing one orbit every 225 million years. But this orbit isn't perfectly circular. The Sun also oscillates up and down through the galactic plane, with a period of about 70 million years, currently moving upward at about 7 kilometers per second. This oscillation might be the lingering effect of ancient merger events, the Sun responding to gravitational waves that were set in motion billions of years ago when dwarf galaxies collided with the Milky Way. Every star in the galaxy performs similar dances, complex orbital motions shaped by the gravitational field created by hundreds of billions of stars plus the vast halo of dark matter that surrounds them. But superimposed on these regular orbital motions are the irregular disturbances caused by mergers, stars scattered by ancient collisions, orbital patterns disrupted by passing dwarf galaxies, chemical composition variations created when gas from consumed galaxies mixed with the Milky Way's interstellar medium. The galaxy is not a pristine, orderly structure. It's a dynamic, chaotic system still reverberating from collisions that happened billions of years ago. And more collisions are coming, but galactic cannibalism represents only one form of death that galaxies experience. Another form of cosmic violence involves stars themselves, individual suns that get torn from their homes and ejected into the darkness between galaxies. These hypervelocity stars represent refugees from gravitational disasters, stars moving so fast they're escaping the Milky Way entirely. Most stars orbit the galaxy at speeds around 200 to 250 kilometers per second, velocities that keep them gravitationally bound to the Milky Way for billions of years. But hypervelocity stars move at 500 to 1,000 kilometers per second or even faster, speeds that exceed the galaxy's escape velocity. These stars are leaving the Milky Way forever, ejected by catastrophic gravitational encounters that gave them enough energy to break free. The primary mechanism for creating hypervelocity stars involves the supermassive black hole at the center of the Milky Way, a monster called Sagittarius A star, that contains 4 million solar masses compressed into a region smaller than our solar system. When binary star systems wander too close to this black hole, tidal forces can tear them apart. One star falls toward the black hole, captured by its gravitational field. The other star gets flung outward at tremendous speed, carrying away the orbital energy of the disrupted binary system. This gravitational slingshot effect can accelerate stars to speeds exceeding 1,000 kilometers per second, fast enough to cross the entire galaxy in less than 100 million years. Once ejected, these stars travel on ballistic trajectories that take them out of the galactic disk, through the halo, and eventually into intergalactic space. They become rogue stars, wandering the void between galaxies with no home to return to. Astronomers have identified hundreds of hypervelocity star candidates, stars moving at speeds inconsistent with normal galactic orbits. Most of these stars are still within the Milky Way, travelling through the halo on outbound trajectories that will eventually take them into intergalactic space. But a few have already escaped, crossing beyond the galaxy's gravitational boundary and entering the vast emptiness between the Milky Way and other galaxies. These rogue stars carry memories of the violence that created them. They were born in the galactic disk, lived normal stellar lives for millions or billions of years, and then experienced a catastrophic gravitational encounter that flung them into exile. From their perspective, if stars could have perspectives, they're falling away from the Milky Way forever, watching the galaxy shrink behind them as they travel through increasingly empty space. The journey of a hypervelocity star takes it through strange environments. After leaving the galactic disk, it passes through the halo, a region populated by old stars and ancient globular clusters. The halo is much less dense than the disk, with vast distances between stars. A hypervelocity star moving through the halo would see the Milky Way's disk recede below it, the familiar spiral structure gradually appearing in its true form as the star gains altitude above the galactic plane. Eventually, the hypervelocity star crosses beyond the visible boundary of the Milky Way, entering the dark matter halo that extends perhaps 1,000,000 light-years from the galactic center. This region is essentially empty of normal matter, containing only the invisible dark matter that makes up most of the galaxy's mass. The star continues its journey through this dark halo, still technically within the Milky Way's gravitational influence, but so far from other stars that it might as well be in intergalactic space. Finally, after travelling for tens of millions of years, the hypervelocity star crosses the boundary where the Milky Way's gravitational field becomes weaker than the collective pull of other galaxies in the local group. At this point, the star has truly escaped. It becomes an intergalactic wanderer, travelling through the vast spaces between galaxies where matter is measured in atoms per cubic meter, rather than stars per cubic light year. The fate of hypervelocity stars depends on their ultimate velocities. Some are moving fast enough to escape not just the Milky Way but the entire local group of galaxies, travelling outward into the cosmic voids that separate galactic clusters. These stars will spend the rest of their lives in complete isolation, billions or trillions of years drifting through space so empty that they might not encounter another star for the entire lifetime of the universe. Other hypervelocity stars are moving fast enough to escape the Milky Way, but not fast enough to escape the local group. These stars will eventually be captured by other galaxies, falling into the gravitational fields of the Andromeda galaxy, or one of the dozens of smaller galaxies that populate our cosmic neighbourhood. They become cosmic immigrants, stars born in the Milky Way but ultimately joining other galactic populations. The existence of hypervelocity stars reveals that galaxies are not closed systems. Stars can escape, matter can be lost. The gravitational catastrophes that eject hypervelocity stars represent a form of mass loss for galaxies, a bleeding away of stellar material into intergalactic space. Over billions of years, this process might become significant, with galaxies losing a measurable fraction of their stellar populations to hypervelocity ejection. But hypervelocity stars aren't the only refugees from gravitational disasters. Some stars get ejected from the galactic disk through different mechanisms, travelling at slower speeds, but still fast enough to reach unusual locations. These stars, sometimes called runaway stars, move at 30 to 200 kilometers per second, relative to the local stellar population, velocities that can carry them out of the disk and into the halo over millions of years. Runaway stars can be created through several mechanisms. Supernova explosions in binary systems can eject the surviving companion star at high velocity. Three-body encounters in dense stellar regions can result in one star being gravitationally slingshot away. Close encounters with molecular clouds can perturb stellar orbits, and the general dynamical evolution of the galactic disk naturally produces a population of stars with unusual velocities. These runaway stars populate the galactic halo, creating a diffuse population of relatively young stars in regions where only old stars should exist. Their presence in the halo reveals the dynamic nature of the galactic disk, the constant churn of stellar motions that occasionally eject stars into regions where they don't belong. The overall picture emerging from studies of stellar streams, hypervelocity stars and runaway stars is one of a galaxy in constant turmoil. The Milky Way appears peaceful from our perspective, the stars slowly wheeling through their orbits in stately patterns that change only over millions of years. But this appearance masks the underlying violence. Stars are constantly being scattered by gravitational encounters. Dwarf galaxies are being torn apart by tidal forces. Hypervelocity stars are being ejected into intergalactic space. The galaxy is not a stable, eternal structure, but a dynamic system where matter flows, Stars move and structures constantly change. And this violence extends beyond individual stars to affect entire stellar populations. When dwarf galaxies merge with the Milky Way, they don't just add their stars to the galactic census. They also trigger bursts of star formation as gas clouds from the two galaxies collide and compress. These starburst events can produce thousands or millions of new stars in relatively short periods, dramatically altering the stellar population of the regions where they occur. The Gaia-Enceladus merger 10 billion years ago likely triggered massive star formation throughout the young Milky Way. When the dwarf galaxy's gas collided with the Milky Way's interstellar medium, the compression created ideal conditions for gravitational collapse. Vast molecular clouds condensed into new stars, producing a generation of stellar systems that all formed during the same brief period of cosmic time. You can still see evidence of this ancient starburst in the ages of stars throughout the galactic halo. Many halo stars show ages clustering around 10 billion years, suggesting they all formed during or shortly after the Gaia-Enceladus merger. This generation of stars represents the children of cosmic violence, suns born from the collision of galaxies. Similar starburst events occurred during other merger events throughout the Milky Way's history. Each time a dwarf galaxy crashed through the galactic disk, it compressed gas clouds and triggered star formation. The cumulative effect of these mergers has been to shape the star formation history of the entire galaxy, creating generations of stars separated by quiet periods when merger activity was low. The future collision with the Large Magellanic Cloud in 2.5 billion years will trigger another massive starburst event. When the dwarf galaxy plunges through the Milky Way's disk, gas clouds from both galaxies will collide at relative velocities of hundreds of kilometers per second. The compression will be violent enough to trigger gravitational collapse across vast regions, producing perhaps billions of new stars in a burst of formation that will briefly double or triple the Milky Way's normal star formation rate. These newly formed stars will light up the galactic disk, creating brilliant blue regions where massive young stars pump out ultraviolet radiation. From a distance, the collision would appear as a sudden brightening of the Milky Way, a galactic-scale fireworks display as two cosmic structures collide and merge. But star formation represents only one consequence of galactic mergers. Another critical effect involves the redistribution of dark matter. When dwarf galaxies are consumed, their dark matter halos get torn apart and mixed into the Milky Way's dark matter distribution. This process can create complex substructures in the dark matter halo, regions where the density varies in ways that don't match the smooth distribution predicted by simple models. Astronomers study these dark matter substructures by looking for their gravitational effects on stars and gas. Regions of enhanced dark matter density create subtle gravitational anomalies that affect stellar orbits. By mapping these anomalies, researchers can reconstruct the distribution of dark matter throughout the galactic halo, revealing the invisible remnants of consumed dwarf galaxies. The discovery that dark matter doesn't form a smooth halo, but instead contains streams, clumps, and other substructures has profound implications for dark matter physics. These substructures might affect the rate at which dark matter particles collide and annihilate, potentially creating detectable signals that could reveal the nature of dark matter itself. They also affect the formation and evolution of stellar structures, creating gravitational environments that influence how stars form and how they move through the galaxy. But perhaps the most disturbing aspect of galactic cannibalism isn't what it tells us about the past, it's what it reveals about the future. The Milky Way's consumption of dwarf galaxies represents the ongoing death of cosmic structures, the systematic erasure of worlds that existed for billions of years, and this process isn't ending, it's accelerating. 15-minute hook point, word count, just tossing at the 800. The Milky Way and Andromeda are on a collision course. In 4 billion years, these two giant spirals will collide in the most spectacular merger our cosmic neighbourhood has ever witnessed. But before we explore that apocalyptic future, we need to understand what's happening right now at the heart of our galaxy. Because the monster that lives there, Sagittarius, a star, is already writing the prologue to the Milky Way's death. Deep in the galactic core, hidden behind vast clouds of gas and dust that block visible light, sits an object so massive and so dense that it warps space-time itself. Sagittarius, a star, the supermassive black hole at the centre of the Milky Way, contains 4 million times the mass of our Sun compressed into a region smaller than Mercury's orbit. This cosmic monster exerts gravitational influence across thousands of light years, shaping the orbits of millions of stars and serving as the gravitational anchor that holds the entire inner galaxy together. But Sagittarius A star isn't just sitting quietly at the galactic centre, it's active, feeding, growing, consuming stars and gas clouds that wander too close to its event horizon. And the violence of this feeding process creates some of the most extreme physics in the observable universe. Astronomers have watched stars orbit Sagittarius A star for decades, tracking their motions with such precision that they can test general relativity in the strongest gravitational field accessible to observation. One star, designated S2, orbits the black hole every 16 years on an elliptical path that brings it to within just 120 astronomical units of the event horizon. At closest approach, S2 travels at 3% of the speed of light, moving so fast through such intense gravitational curvature that relativistic effects become measurable. The orbit of S2 doesn't close. It precesses, rotating slowly around the black hole like a spinning top. This orbital precession matches the predictions of general relativity with extraordinary precision, confirming Einstein's theory in an environment where gravity is millions of times stronger than anywhere in our solar system. But the measurements also reveal something disturbing. The gravitational field around Sagittarius A star is so intense that space-time itself becomes unstable under certain conditions. When massive stars in the galactic centre die, they don't always leave behind neutron stars or smaller stellar mass black holes. Sometimes they're shredded by tidal forces before they can collapse, torn apart by the gravitational gradient around Sagittarius A star. The outer layers of these dying stars get stretched and pulled, transformed into long streams of gas that spiral inward toward the black hole's event horizon. This process, called tidal disruption, creates spectacular flares of radiation as the stellar material heats up during its final infell. The gas reaches temperatures of millions of degrees, hot enough to emit X-rays and gamma rays that blast outward from the dying star's remnants. For a brief period lasting weeks or months, the tidal disruption event outshines every other source of radiation in the galactic centre, a cosmic scream marking the death of a star. Sagittarius A star consumes these disrupted stars slowly, feeding on the gas streams over timescales of months to years. But occasionally, the black hole encounters something it cannot immediately consume. Massive molecular clouds, dense knots of gas and dust containing thousands or millions of solar masses can survive close encounters with Sagittarius A star if they're moving fast enough or if their internal structure is strong enough to resist tidal shredding. When these clouds pass near the black hole, they experience gravitational forces intense enough to compress their internal structure, triggering bursts of star formation within the cloud itself. These newborn stars enter existence already doomed, orbiting so close to Sagittarius, a star, that tidal forces will eventually tear them apart just like their molecular cloud parents. They live brief, violent lives before being consumed by the black hole that triggered their formation. The region immediately surrounding Sagittarius, a star, within a few light years of the event horizon, is one of the most dangerous environments in the galaxy. Intense gravitational forces, powerful radiation from infalling matter, and occasional outbursts from the black hole's accretion disk create conditions that would shred any normal stellar system in moments. And yet dozens of young, massive stars orbit within this death zone, travelling on trajectories that bring them within light months of the event horizon. How these stars formed in such a hostile environment remains one of the great mysteries of galactic astronomy. The conventional process of star formation requires cold, dense molecular clouds that can collapse under their own gravity. But the region near Sagittarius A star is bathed in intense radiation and gravitational tides that should prevent cloud collapse. The stars shouldn't exist, and yet they do, orbiting the black hole in a cosmic dance that will eventually lead to their destruction. Some of these stars are members of binary systems, two stars orbiting each other while also orbiting the black hole. These binaries face an even stranger fate. When they pass close to Sagittarius A star, tidal forces can disrupt the binary, capturing one star while ejecting the other at hypervelocity. This is one of the primary mechanisms for creating the hypervelocity stars that escape the galaxy entirely, gravitational catastrophes in the galactic center that fling stars into intergalactic space at speeds exceeding 1,000 kilometers per second. The stars that survive these close encounters carry scars from their brushes with death. Their atmospheres are stripped away by radiation and tidal forces. Their orbits are perturbed by gravitational interactions with other stars and with the black hole itself. Some are compressed by tidal forces, transformed into shapes more ellipsoidal than spherical. Others are heated to temperatures far higher than their luminosity would normally create, energized by the harsh radiation environment near the galactic center. But Sagittarius A star's influence extends far beyond the stars orbiting within a few light years of the event horizon. The black hole shapes the entire structure of the galactic bulge, the dense concentration of stars that forms the central region of the Milky Way. Stars throughout the bulge orbit in complex patterns influenced by the black hole's gravitational field, creating what astronomers call triaxial bulge structure, a three-dimensional arrangement of stellar orbits that doesn't match the simple rotating disk pattern found in the outer galaxy. The black hole also influences the distribution of gas throughout the inner galaxy. Molecular clouds that venture too close get stretched by tidal forces, transformed into elongated streamers that follow specific orbital paths determined by the gravitational field. These gas streamers create a complex web of material throughout the galactic center, a cosmic infrastructure of cold gas that will eventually feed future generations of stars or fall into Sagittarius A star itself. Recent observations have revealed that Sagittarius A star isn't always quiet. The black hole experiences irregular outbursts where its brightness increases by factors of 10 to 100 for periods lasting hours or days. These flares result from material in the accretion disk suddenly falling into the black hole, releasing bursts of radiation as it crosses the event horizon. The flares reveal something disturbing about the black hole's feeding behavior. Sagittarius A star doesn't consume matter steadily. Instead, it feeds chaotically, ingesting clumps and streams of material whenever they happen to arrive. This irregular feeding creates unpredictable outbursts that can temporarily double or triple the radiation output from the galactic center. During these outburst periods, the environment near Sagittarius A star becomes even more hostile than usual. Radiation levels spike, particle acceleration increases, the magnetized plasma in the accretion disk becomes turbulent, creating powerful magnetic fields that can accelerate particles to near light speed. Any stellar system within a few light years of the black hole during one of these outbursts would be bathed in dangerous levels of radiation, potentially stripping away atmospheres or damaging any hypothetical planets orbiting stars in this region. The chaotic nature of these outbursts suggests that Sagittarius A star's accretion disk operates in a fundamentally different regime than the steady accretion seen around some other supermassive black holes. Instead of a smooth inflow of material, the black hole feeds on discrete clumps of gas and occasional disrupted stars, creating an erratic feeding pattern that produces irregular bursts of activity. This chaotic feeding behavior might be typical of supermassive black holes and galaxies that aren't experiencing major merger events. When galaxies collide, gas from both systems falls toward the central black hole, creating a steady stream of fuel that powers sustained quasar activity. But in between major mergers, black holes like Sagittarius A star must survive on scraps, occasional molecular clouds or disrupted stars that wander close enough to be consumed. The black hole is starving, and its hunger will only grow as the galaxy evolves. Over billions of years, the gas supply in the galactic center will be consumed by star formation or ejected by supernova explosions and stellar winds. Sagittarius A star will have less and less material to feed on, entering an increasingly quiescent state where major feeding events become rare. But this starvation won't last forever. In 4 billion years, when the Milky Way collides with Andromeda, massive amounts of gas will be funneled toward the galactic centers of both galaxies. Sagittarius A star will suddenly find itself with access to fuel reservoirs far larger than anything it's consumed in billions of years, and when that happens, the black hole will awaken. The collision between the Milky Way and Andromeda will ultimately result in the merger of their central black holes, Sagittarius A star and Andromeda's even more massive central black hole, a 100 million solar mass monster that dwarfs our relatively modest galactic core. When these two black holes finally spiral together and merge, they will create gravitational waves powerful enough to be detected by spacecraft anywhere in the galaxy. The merger will release more energy in a few seconds than the Sun will produce in its entire 10 billion year lifetime. But before that ultimate collision, both black holes will experience a feeding frenzy as gas from the galactic merger funnels toward them. This will transform both galaxies into active galactic nuclei, cosmic structures where the central black holes outshine every star in their host galaxies combined. For a period lasting millions of years, the merging Milky Way and Andromeda will become a double quasar system, twin beacons of radiation powered by supermassive black holes, consuming galactic-scale amounts of gas. From Earth's perspective, if Earth still exists in any meaningful form 4 billion years from now, the activated Sagittarius A star will appear as a brilliant point of light in the direction of the galactic center, easily visible to the naked eye despite being hidden behind dust clouds. The black hole's accretion disk will emit so much radiation that it will temporarily become the brightest object in the galaxy other than the Sun itself. This feeding frenzy will fundamentally alter the environment throughout the inner galaxy. Radiation from the active galactic nucleus will heat gas throughout the galactic bulge, potentially preventing star formation in the central regions for millions of years. Powerful jets of accelerated particles might erupt from the black hole's poles, blasting through the galactic disk and creating vast bubbles of hot gas that expand into the halo. The radiation will also affect planetary systems throughout the inner galaxy. Planets orbiting stars within a few thousand light-years of Sagittarius A star might be sterilized by the intense radiation, their atmospheres stripped away or their surfaces scoured by energetic particles. Any hypothetical civilizations in the galactic center would face an existential crisis as their environment transforms from the relatively benign conditions found in normal spiral galaxies to the hostile radiation environment surrounding an active galactic nucleus. But the activation of Sagittarius A star represents only one chapter in the story of the Milky Way's death. The collision with Andromeda will destroy the galaxy in ways far more fundamental than the temporary activation of the central black hole. The entire structure of the Milky Way will be torn apart and rebuilt, transformed from a spiral galaxy into something entirely different. Before we explore that apocalyptic collision in detail, we need to understand what's already happening in the space between galaxies. Because the death of the Milky Way isn't just about our galaxy and Andromeda, it's about the entire local group of galaxies, dozens of stellar systems that are all gravitationally bound together and all heading toward the same ultimate fate. Word count, chapter 13 to 200. The night sky you see is a lie. A comforting illusion that masks the true violence of cosmic motion. When you look up on a clear evening and see the stars scattered across the darkness, they appear static, eternal, unchanging. But every one of those points of light is moving, racing through space at hundreds of kilometers per second, participating in gravitational dances that will ultimately reshape the entire cosmic neighborhood. The Milky Way sits at the center of what astronomers call the local group, a gravitationally bound collection of more than 80 galaxies spread across roughly 10 million light-years of space. Most of these galaxies are dwarfs, small stellar systems containing only a few billion stars. But three galaxies dominate the local group through their sheer mass: the Milky Way, Andromeda, and Triangulum, a smaller spiral galaxy that will ultimately be consumed by one of the larger systems. All of these galaxies are moving, orbiting their common center of mass, falling toward each other under mutual gravitational attraction. And the motions aren't random. They're following trajectories determined by billions of years of gravitational evolution, paths that will culminate in a series of mergers that will transform the entire local group into something entirely different. The Andromeda galaxy is approaching the Milky Way at 110 kilometers per second, closing a gap of 2.5 million light-years at a rate that will result in first contact in approximately 4 billion years. But that headline velocity masks the true complexity of the motion. Andromeda isn't just moving toward us, it's also moving sideways, travelling at about 20 kilometers per second perpendicular to the line connecting the two galaxies. This tangential velocity means the collision won't be head-on. Instead, the two galaxies will approach each other at an angle, their disks tilted relative to each other when they first make contact. This off-center collision will create asymmetric tidal forces, stretching one side of each galaxy more than the other, and creating the long tidal tails that simulations predict will extend hundreds of thousands of light-years into intergalactic space. The first contact between the Milky Way and Andromeda will be gentle, almost imperceptible to any observers in either galaxy. The leading edges of the two dark matter halos, vast spherical distributions of invisible matter that extend far beyond the visible disks, will begin to overlap. Individual stars from the outer regions of both galaxies will start feeling gravitational influences from the other system, their orbits perturbed by forces that didn't exist a billion years earlier. But this gentle beginning will accelerate into violence. As more of the two galaxies' masses overlap, the gravitational forces will intensify. Stars in the outer disks will be pulled toward the other galaxy, creating streams of matter that bridge the gap between the two systems. Gas clouds will collide where the interstellar media of both galaxies meet, compressing and heating to temperatures that trigger massive bursts of star formation. The first pass between the two galaxies won't result in a clean merger. Instead, the galaxies will pass through each other, their stars and gas interpenetrating but not immediately mixing. This might seem counterintuitive, but galaxies are mostly empty space. The average distance between stars in a galactic disk is about 5 light-years. When two disks pass through each other, the overwhelming majority of stars simply sail past each other without direct interaction. But the gravitational effects are profound. Each galaxy's passage through the other pulls matter along with it, stretching both systems into elongated shapes. The beautiful spiral structures that characterize both the Milky Way and Andromeda will be destroyed during the first pass, their arms pulled apart and reformed into long streamers that trail behind each galaxy as they separate. After the first pass, the two galaxies will move apart, travelling perhaps 1 million light-years before their mutual gravitational attraction slows their separation and pulls them back together. This turnaround process takes hundreds of millions of years, time for the gravitationally disturbed stars and gas to settle into new temporary configurations. But the respite is brief. Soon the galaxies are falling back toward each other for a second collision. The second pass is more violent than the first. More matter has been pulled into elongated tidal tails during the initial encounter, and these tails now crash together as the galaxies recollide. Additional star formation is triggered where gas streams collide. More stars are scattered into the growing halo of material surrounding both systems. The gravitational binding energy of both galaxies decreases as their orbits decay, spiraling toward an eventual final merger. A third pass might occur, or even a fourth, depending on the exact parameters of the collision. But each passage removes energy from the system, and eventually the two galaxies no longer have enough momentum to separate. They settle into a combined structure, a single gravitationally bound system that will take billions of additional years to fully relax into equilibrium. The final product of this merger won't be a spiral galaxy. Simulations consistently show that major mergers between spiral galaxies produce elliptical galaxies, systems where stars orbit in random directions rather than following the organized disk structure seen in spirals. The combined Milky Way and Andromeda system, sometimes called Milkomeda or Milkdromeda in the literature, will be a giant elliptical galaxy containing roughly 1 trillion stars, all orbiting the merged central black hole in chaotic patterns that bear no resemblance to the original spiral structures. This transformation from spiral to elliptical represents a fundamental change in galactic character. Spiral galaxies are active, star-forming systems with organized structure and ongoing chemical evolution. Elliptical galaxies are largely dead, containing mostly old stars with little ongoing star formation and no organized disk structure. The merger will effectively kill both the Milky Way and Andromeda as functioning spiral galaxies, transforming them into a stellar graveyard populated by aging suns slowly fading into darkness. But the death of the spiral structure isn't the most dramatic consequence of the collision. The real violence occurs in the cores of both galaxies, where the supermassive black holes at their centres begin a deadly spiral toward merger. When the Milky Way and Andromeda first collide, their central black holes will be separated by millions of light years, too far apart to directly influence each other. But as the galaxies pass through each other repeatedly, the black holes trace complex orbits through the combined system, each passage bringing them closer together. Eventually, after billions of years and multiple galactic encounters, the black holes will find themselves orbiting each other at distances measured in thousands of light years rather than millions. At this point, a new physical process takes over. The black holes begin to interact with the stars in their vicinity through a process called dynamical friction. As each black hole orbits through the stellar population, it gravitationally attracts nearby stars, creating a slight overdensity of stars in its wake. This overdensity acts like a drag force, slowly removing orbital energy from the black hole and causing its orbit to decay. Think of it like a massive object moving through a viscous fluid. The black hole's gravity pulls stars along with it, and those stars pull back on the black hole, slowing it down and causing it to spiral inward. The process is slow, taking hundreds of millions of years to bring the black holes from galactic scale separations down to distances of a few light years. But dynamical friction becomes less effective at close separations. When the black holes are only a few light years apart, there aren't enough stars in the immediate vicinity to continue extracting orbital energy efficiently. The black holes can stall at this separation, trapped in what's called the final parsec problem, unable to merge because the mechanism that brought them this close no longer works efficiently. However, theoretical work suggests several ways the black holes can bridge this final gap. Gas flowing toward the galactic centre can carry away orbital energy through gravitational torques. Triple star interactions, where a star approaches close enough to the binary black hole system to gravitationally interact with both objects, can eject the star at high velocity while removing energy from the black hole's orbit. And gravitational waves, ripples in space-time created by the orbiting black holes, carry away energy and angular momentum, slowly but inexorably drawing the black holes together. Once the black holes reach separations of about 1/10 of a light year, gravitational wave emission becomes the dominant mechanism for orbital decay. At this point, the black holes are orbiting each other thousands of times per year, and the gravitational waves they emit carry away significant amounts of energy. The orbit shrinks noticeably over timescales of millions of years rather than billions, As the black holes spiral closer, the gravitational wave emission intensifies. At separations of light weeks, they're orbiting millions of times per second, emitting gravitational waves at frequencies detectable by space-based observatories. At separations of light hours, the gravitational waves become powerful enough to affect the surrounding environment, creating ripples in space-time that perturb stellar orbits throughout the galactic center. And then, in the final seconds before merger, the black holes enter a regime of truly extreme physics. The two event horizons, each representing a point of no return where escape velocity exceeds the speed of light, approach each other at relativistic speeds. Space and time around the black holes become so warped that the usual concepts of distance and duration break down. The black holes aren't just orbiting in curved space-time, they're orbiting through space-time that's curving so rapidly it's almost churning. The final merger lasts only seconds, but releases more energy than all the stars in the observable universe emit over the same period. The gravitational waves peak at frequencies of a few hundred hertz, carrying away 3 solar masses worth of energy in the form of space-time ripples that propagate outward at the speed of light. These waves are powerful enough to be detected by spacecraft anywhere in the galaxy, creating measurable distortions in the distances between objects as they pass. The merged black hole, containing approximately 104 million solar masses, the combined mass of Sagittarius A star and Andromeda's central black hole, minus the 3 solar masses radiated away as gravitational waves, settles into a final configuration. But it doesn't settle quietly. The merger imparts a kick to the combined black hole, a recoil velocity that can reach hundreds or even thousands of kilometers per second, depending on the spin properties and orbital configuration of the original black holes. This kick velocity results from asymmetric emission of gravitational waves during the merger. If the black holes are spinning, and their spins are misaligned with the orbital angular momentum, the gravitational waves are emitted preferentially in certain directions, creating a net momentum that pushes the merged black hole away from the center of mass. In extreme cases, this recoil velocity can be large enough to eject the merged black hole from the galaxy entirely, sending it wandering through intergalactic space carrying 100 million solar masses of invisible matter. Most likely the kick velocity won't be quite that extreme. More typical recoil velocities of a few hundred kilometers per second would displace the merged black hole from the galactic center, but not eject it entirely. The black hole would oscillate back and forth through the galactic core for millions of years, gradually settling back toward the center as dynamical friction with stars removes the excess velocity. But during this oscillation period, the galactic center would lack a stationary supermassive black hole, creating unusual gravitational conditions that would affect stellar orbits throughout the inner galaxy. Stars that had been orbiting Sagittarius A star would suddenly find themselves orbiting an off-center black hole, their orbital parameters completely changed by the displacement. The merger of the central black holes represents one of the most violent events that can occur in a galaxy. But it's not the only catastrophic consequence of the Milky Way Andromeda collision. Throughout both galaxies, stellar systems will be disrupted, planetary systems destroyed, and entire regions sterilized by radiation from triggered star formation. 30-minute hook point, word count 19,700. If Earth still exists 4 billion years from now, the night sky will transform into something unrecognizable. The Andromeda galaxy, currently a faint smudge visible only from dark locations far from city lights, will dominate the heavens, growing larger with each passing millennium, stretching across the sky in a vast spiral that eventually fills half the celestial sphere. And then, as the two galaxies interpenetrate, the sky will become a chaos of stellar clouds, glowing gas and nebulae brighter than anything visible in our current night sky. But Earth's survival through the collision is far from certain, not because of direct collisions with stars from Andromeda, though such impacts aren't completely impossible. No, the real threats come from more subtle dangers, gravitational perturbations that could destabilize the solar system, radiation from massive starbursts triggered by the collision, changes in the galactic environment that make our region of space inhospitable to planetary systems. The Sun orbits the Milky Way at a distance of about 26,000 light-years from the galactic centre, placing our solar system in what's typically considered a safe location in the outer disk. But safety is relative. When the Milky Way and Andromeda collide, stellar orbits throughout both galaxies will be violently perturbed. Some stars will be flung into the galactic halo, scattered by gravitational encounters with density waves propagating through the merging systems. Others will be driven inward toward the galactic centre, their orbits radically altered by the gravitational chaos of the collision. Computer simulations of the merger suggest about a 12% chance that our solar system will be ejected from the galactic disk entirely during the collision, flung into the halo, or even into intergalactic space by gravitational interactions with density waves or close encounters with stars from Andromeda. If this happens, Earth would find itself in an increasingly empty region of space, the familiar band of the Milky Way gradually fading as the Sun drifts away from the galactic disk into the dark spaces of the halo. From one perspective, ejection might seem catastrophic. The solar system would be isolated, separated from the stellar community it's been part of for 9 billion years by the time the collision occurs. But from another perspective, ejection might be the safest possible outcome. The halo is a quiet, empty region, far from the violence occurring in the galactic disk. A planetary system ejected into the halo would avoid the radiation from starbursts, the gravitational perturbations from density waves, and the increased risk of stellar encounters that will plague systems remaining in the disk. But ejection is the minority outcome. Most simulations suggest an 88% chance that the solar system remains within the merged galaxy's disk, though not necessarily in the same location relative to the galactic centre. The Sun's galactocentric distance could increase or decrease by thousands of light-years, depending on the specifics of how density waves propagate through the merging systems. Being relocated to a different part of the galactic disk carries its own risks. Regions closer to the galactic centre experience higher stellar densities, increasing the probability of close encounters with passing stars. These encounters wouldn't typically result in direct collisions. Stars are too small and too far apart for that, but they could gravitationally perturb the outer solar system, potentially destabilizing the orbits of planets in the outer regions or scattering comets from the Oort cloud toward the inner system. A single stellar encounter probably wouldn't be catastrophic for Earth itself. The inner planets orbit close enough to the Sun that their orbits are dominated by the Sun's gravity and largely immune to perturbations from passing stars. But the outer planets, Jupiter, Saturn, Uranus, Neptune, sit at distances where passing stars could gravitationally interact with them, potentially altering their orbits over the course of a close encounter. The bigger risk comes from the increased radiation environment during the starburst phases of the merger. When gas clouds from the two galaxies collide, they compress and heat, triggering gravitational collapse and forming new stars at rates potentially 10 to 100 times higher than the current star formation rate in either galaxy. These starburst regions light up with young, massive stars that pump out enormous amounts of ultraviolet radiation. Massive stars live fast and die young. The most massive stars, containing 20 to 100 solar masses, burn through their hydrogen fuel in only a few million years before exploding as supernovae. During a starburst event, thousands or millions of these massive stars form in relatively small regions of space, all destined to explode as supernovae within a few million years of each other. A single supernova occurring within 30 light-years of the solar system could damage Earth's ozone layer through radiation exposure, potentially causing mass extinction events. During a starburst phase of the galactic merger, the supernova rate in starburst regions could be hundreds of times higher than in normal stellar populations, creating a statistically significant risk that the solar system might find itself near one of these explosions. The danger isn't the explosion itself, Supernova shockwaves expand at thousands of kilometers per second, fast by terrestrial standards, but still requiring thousands of years to cross interstellar distances. By the time a supernova shockwave reaches a distance of 30 light-years, it's been diluted by expansion to the point where it poses little direct threat to planetary systems. No, the real danger comes from the radiation. Supernova explosions emit tremendous amounts of gamma rays, X-rays and cosmic rays, high-energy particles accelerated to near-light speed by the explosion's shockwave. These particles can penetrate planetary atmospheres and damage ozone layers, the protective shields that filter dangerous ultraviolet radiation from stellar sources. Earth's ozone layer has protected complex life on the surface for hundreds of millions of years, absorbing ultraviolet radiation that would otherwise sterilize the surface. But supernova radiation can temporarily destroy ozone through chemical reactions, creating holes in the protective layer that allow dangerous levels of ultraviolet radiation to reach the surface. Life on Earth has survived close supernova events in the past. Mass extinction events in the geological record show correlations with nearby supernovae. But each event represents a crisis that life must survive through adaptation or die. During the starburst phases of the galactic merger, the supernova rate within the solar system's vicinity could increase dramatically if our solar system happens to be relocated near one of the starburst regions. The probability of a close supernova occurring within any given million-year period could increase from the normal background rate of roughly 1 per 100 million years to potentially 1 per million years or even higher. Over the billions of years that the merger takes to complete, this increased supernova rate represents a genuine existential risk to complex life on Earth. Assuming Earth remains habitable on other grounds, each close supernova would force life to adapt to increased radiation levels or face extinction. Over many such events, the cumulative stress might eliminate species that would otherwise survive in normal galactic environments. But supernovae aren't the only radiation threat. The intense star formation occurring during starburst phases also creates vast clouds of ionizing radiation from young, hot stars. These massive stars emit most of their light in the ultraviolet part of the spectrum, radiation that can ionize hydrogen gas across thousands of light-years of space, creating bright emission nebulae visible throughout the merging galaxies. From Earth's perspective, if the solar system ends up near one of these starburst regions, the night sky would be dominated by glowing nebulae stretching across the heavens. Beautiful, certainly, but also dangerous. The same ultraviolet radiation that ionizes interstellar hydrogen can damage biological molecules, creating additional stress for life on any planets located in or near these regions. The combined effects of increased supernova rates, higher ultraviolet radiation from hot young stars, and potential gravitational perturbations from stellar density waves make the merger period a hazardous time for planetary systems in both galaxies. Not every system will be destroyed. Most stars will survive the merger with their planets intact, but the probability of catastrophic events affecting any given system increases substantially during the multi-billion-year process of galactic merger. For hypothetical civilizations existing in either galaxy during the merger, these threats would be foreseeable millions or billions of years in advance. A civilization with technology capable of detecting stellar motions and modeling galactic dynamics could predict the merger and its consequences long before the first dramatic events occur. Such a civilization would face profound choices about how to respond. One option would be migration, physically relocating to safer regions of the galaxy before the worst of the merger violence occurs. Systems in the outer disk might be safer than systems in the inner regions where stellar densities are higher. Or a civilization might choose to abandon the galactic disk entirely, building habitats in the halo or even in intergalactic space where the merger's effects would be minimal. Another option would be technological adaptation, developing methods to protect planetary systems from radiation threats and gravitational perturbations. Artificial ozone layers, planetary magnetic fields enhanced beyond natural levels, space-based radiation shields, gravitational engineering to stabilize orbits against perturbations. A sufficiently advanced civilization might be able to weather the merger without relocating, protecting its home system through technological means. Or a civilization might choose to do nothing, gambling that the statistical risks won't materialize in their particular location. The merger represents increased risk, not certainty of destruction. Most stellar systems will survive relatively unscathed, experiencing the merger as a spectacular light show in the sky, but suffering no direct damage. A civilization might reasonably decide that the probability of catastrophe is low enough to simply accept the risk and focus on other priorities, but for life that isn't technologically advanced enough to predict or respond to the threats, the merger represents an unpredictable extinction filter. Some worlds will be sterilized by nearby supernovae, others will have their ozone layers damaged by intense ultraviolet radiation, some planetary systems will be gravitationally disrupted, their planets scattered or ejected into interstellar space. The merger won't destroy all life in either galaxy, but it will create a period lasting billions of years when life faces increased extinction risk across much of the galactic environment. And throughout all of this, both galaxies' spiral structures are being systematically destroyed, torn apart by tidal forces and rebuilt into something entirely different. The death of a spiral galaxy isn't a single catastrophic event. It's a gradual unraveling that takes billions of years to complete. A slow-motion apocalypse where beautiful organized structure gives way to chaos and eventually to a different kind of order. The spiral arms of the Milky Way and Andromeda, those graceful curves that trace out regions of active star formation and define the galaxy's visual appearance, will be the first structures to die during the merger. Spiral arms aren't permanent features, they're density waves, regions where stars and gas are temporarily compressed as they orbit through the galactic disk. Stars don't stay in spiral arms, they pass through them like cars on a highway passing through a traffic jam, but the density wave itself persists, maintained by the gravitational interactions of billions of stars all influencing each other through their combined gravitational field. When two spiral galaxies collide, their density wave patterns become disrupted. The gravitational field is no longer dominated by a single galaxy's mass distribution, but instead reflects the complex combined gravitational potential of both systems. The original spiral patterns break down. New density waves form and dissolve on timescales of millions of years, and eventually, after multiple passages and billions of years of interaction, the density wave patterns disappear entirely, replaced by the more chaotic gravitational environment of an elliptical galaxy. The destruction of the spiral arms means the end of organized star formation patterns in both galaxies. In a healthy spiral galaxy, most star formation occurs in the density waves that define the arms, where gas clouds are compressed enough to trigger gravitational collapse. But in the chaotic environment of a merging system, star formation becomes distributed throughout the disk, rather than concentrated in specific regions. Later, as the merger progresses and the galaxy's gas supplies are consumed by starburst events or ejected into intergalactic space by supernova-driven winds, star formation decreases dramatically. By the time the merger is complete and Milkomeda has relaxed into an equilibrium configuration, several billion years after the initial collision, star formation has essentially ceased. The galaxy has consumed its gas supply, converting most of it into stars during the starburst phases of the merger, or ejecting it into intergalactic space through feedback from supernovae and stellar winds. What remains is a stellar population dominated by old, low-mass stars, the kind of stars that live for trillions of years, slowly fading as they exhaust their hydrogen fuel. This transformation from a star-forming spiral galaxy to a dead elliptical galaxy represents a fundamental change in galactic metabolism. Spiral galaxies are alive in a sense, continuously forming new stars, evolving chemically as massive stars forge heavy elements and return them to the interstellar medium through supernova explosions, maintaining active disk structures through the interplay of rotation and star formation. Elliptical galaxies are dead, their star-forming days behind them, their stellar populations aging and fading with no new generations of stars to replace them. The merger kills both galaxies as functioning stellar ecosystems and replaces them with a cosmic mausoleum, a vast collection of aging stars slowly burning through the last of their fuel with no prospect of replacement. But even this dead galaxy won't persist forever in its post-merger form. On even longer timescales, measured in hundreds of billions or trillions of years, stellar evolution will continue transforming the merged galaxy in ways that make the original merger seem like a brief transitional phase in a much longer story. The Sun will die long before the full consequences of the merger become apparent. Our star, currently about 4.6 billion years old, has another 5 billion years remaining before it exhausts the hydrogen fuel in its core and begins its transformation into a red giant. This stellar evolution will occur regardless of the galactic merger. The Sun's internal physics operates on timescales completely independent of the galactic environment. In about 5 billion years, roughly a billion years after the initial Milky Way Andromeda collision but billions of years before the merger is complete, the Sun will expand into a red giant star, possibly large enough to engulf the inner planets, including Earth. If Earth survives this phase by virtue of the Sun losing enough mass during its red giant stage to push planetary orbits outward, it will be left as a scorched, lifeless world orbiting a white dwarf remnant, the dense stellar core left behind when the Sun sheds its outer layers. This process of stellar evolution will happen to billions of stars throughout both galaxies during and after the merger. Every star like the Sun will eventually become a red giant and then a white dwarf. More massive stars will end as neutron stars or black holes. The least massive stars, red dwarfs containing less than half the Sun's mass, will live for trillions of years, far longer than the current age of the universe, but even they will eventually exhaust their fuel and fade into cold, dark stellar remnants. Over timescales of hundreds of billions of years, the merged galaxy will transform from a collection of shining stars into a graveyard of stellar remnants. White dwarfs, neutron stars, and black holes will dominate the galactic mass budget, with the remaining active stars being predominantly low-mass red dwarfs, the last stars still burning hydrogen, and on even longer timescales, measured in Google years, 10 to 100 years, even these remnants will decay or evaporate. White dwarfs will slowly cool, eventually becoming black dwarfs, cold, dense objects that emit no light. Black holes will evaporate through Hawking radiation, a quantum mechanical process where black holes slowly lose mass by radiating particles. The merged galaxy will eventually become a dark, cold collection of decayed stellar remnants, drifting through an expanding universe. But that endpoint lies so far in the future that it's almost meaningless to current inhabitants of the Milky Way. The immediate apocalypse, the collision with Andromeda in 4 billion years, is the death that matters on timescales humans can comprehend. Part 2. The countdown to collision. The merger won't happen suddenly. It will unfold over billions of years in a carefully choreographed dance of gravity that astronomers can predict with disturbing precision. Computer simulations of the Milky Way Andromeda collision have been refined over decades, incorporating ever more detailed data about the masses, velocities, and internal structures of both galaxies. And these simulations all tell the same story. The collision is inevitable, the timeline is set, and nothing in the universe can prevent what's coming. Right now, as you process these words, Andromeda is 2.5 million light-years away, approaching at 110 kilometers per second. That sounds like a considerable distance, and by human standards it is. Light travelling from Andromeda takes 2.5 million years to reach Earth, meaning when you look at Andromeda through a telescope, you're seeing the galaxy as it existed when our earliest human ancestors were just beginning to walk upright on the African savanna. But by cosmic standards, 2.5 million light-years is practically next door. And 110 kilometers per second, while slower than many stellar velocities within galaxies, is fast enough to close that gap on a timescale that astronomy considers brief. In approximately 4 billion years, the first contact will occur. The leading edges of the two galaxies' dark matter halos will begin to overlap, and the gravitational binding between the systems will become significant. The dark matter halos extend far beyond the visible disks of both galaxies. While the Milky Way's stellar disk spans about 100,000 light-years, and Andromeda's disk is roughly twice that size, their dark matter halos reach 10 times farther, creating vast invisible spheres of gravitational influence that stretch millions of light-years into space. These dark matter distributions contain roughly 10 times more mass than all the stars in both galaxies combined, and their gravitational fields dominate the large-scale dynamics of the merger. When the dark matter halos first make contact, about 500 million years before the visible disks collide, subtle gravitational perturbations will begin affecting both galaxies. Stars in the outermost regions of each disk will feel new forces, weak but persistent, pulling them toward the other galaxy. These forces won't be strong enough to dramatically alter individual stellar orbits immediately, but over hundreds of millions of years they'll accumulate, slowly reshaping the outer regions of both galaxies. The first visible sign of the impending collision will be tidal distortions in both galaxies' outer regions. Long before the disks actually touch, their mutual gravitational attraction will begin pulling streams of stars and gas away from each galaxy, creating tidal tails that stretch toward the approaching neighbour. These tails will be faint at first, visible only to sensitive telescopes capable of detecting the diffuse light from scattered stars. But they'll grow more prominent as the galaxies draw closer, eventually becoming spectacular features stretching hundreds of thousands of light-years into intergalactic space. From Earth's perspective, assuming Earth and the Sun still exist in any meaningful form, the changes will be gradual enough that no single human lifetime would witness dramatic transformation. But over generations, over centuries and millennia, the changes would become unmistakable. Andromeda would grow larger in the night sky, year by year, decade by decade. The fuzzy blob visible from dark locations would expand, eventually becoming large enough to show structure to the naked eye. Spiral arms would become visible without telescopes. Individual star clusters in Andromeda would resolve into discrete points of light. 3.5 billion years from now, about 500 million years before first contact, Andromeda will fill a substantial fraction of the night sky. Instead of appearing as a small smudge in the constellation Andromeda, it will span dozens of degrees, a vast spiral visible from dusk to dawn for half the year. The view will be spectacular, but also unsettling. The growing presence of another galaxy dominating the sky will make it impossible to ignore that the cosmic neighbourhood is changing, that the familiar structure of the universe is being rearranged by forces beyond any control. But the spectacular views are just beginning. As the galaxies close to within a few 100,000 light-years, about 100 million years before first contact, the tidal distortions will become dramatic. Both galaxies will develop long streamers of stars pulled toward each other by mutual gravitational attraction. These tidal tails will be visible as faint bridges of light connecting the two galaxies, cosmic threads linking worlds that are about to collide. The first actual collision, when the outer regions of the visible disks make contact, will occur approximately 3.75 billion years from now. But this won't be a single catastrophic moment. Galaxy collisions unfold over hundreds of millions of years, and what observers would witness is a gradual interpenetration, where the two systems pass through each other like two clouds of mist merging in slow motion. When the leading edges of the disks first touch, The immediate effect will be compression of interstellar gas clouds where the two galaxies' interstellar media collide. Gas clouds in the outer disks, moving at hundreds of kilometers per second relative to each other, will crash together with enough energy to heat them to millions of degrees. This compression will trigger gravitational collapse in some regions, igniting bursts of star formation as compressed gas clouds reach densities high enough for fusion to begin. The first starburst regions will light up in the collision zone like cosmic fireworks, clusters of young, hot, massive stars forming in regions where the two galaxies' gas supplies have compressed and heated. These starburst clusters will emit intense ultraviolet radiation, ionizing the surrounding gas and creating brilliant emission nebulae that glow with the light of hydrogen atoms recombining after being stripped of their electrons. From a distance, if hypothetical observers were watching from a nearby galaxy, the collision would appear as bright knots of light developing where the two galactic disks overlap. These bright regions would expand as more gas clouds collide, creating crescents and arcs of active star formation, tracing the interface between the two systems. The combined luminosity of the merging galaxies would increase substantially during this phase, the new stars adding their light to the billions of existing stellar populations. But the majority of stars in both galaxies wouldn't notice the collision directly. Stars are so small compared to the spaces between them that direct collisions between individual stars are extraordinarily rare even during galaxy mergers. When two galaxy disks interpenetrate, the overwhelming majority of stars simply pass by each other. Their individual gravitational influence is too weak to significantly alter each other's trajectories at the large separations typical of stellar encounters. However, the collective gravitational field of each galaxy profoundly affects the other. As the disks pass through each other, the gravitational potential changes for every star in both systems. Stars that were in stable circular orbits suddenly find themselves in gravitational fields that are no longer symmetric. The smooth gravitational potential that maintained their circular orbits is disturbed by the presence of billions of stars from the other galaxy, creating perturbations that alter stellar velocities and orbital shapes. These gravitational perturbations will scatter stars throughout both galaxies. Some stars in the inner regions of each disk will be accelerated, gaining enough velocity to move to larger orbital radii. Others will be decelerated, falling toward the galactic cores. The net effect is to heat the stellar populations, increasing the random velocities of stars and puffing up the disks from relatively thin structures into thicker, more bloated configurations. The beautiful spiral arms that characterize both galaxies will be destroyed during the first passage. Spiral arms are density waves, patterns maintained by gravitational resonances in rotating galactic disks. When two disks interpenetrate, the gravitational disturbances destroy these resonance patterns, dissolving the spiral arms into irregular structures that no longer trace clean logarithmic spirals. After the first passage, both galaxies will appear disturbed, their formerly graceful spiral patterns replaced by chaotic arrangements of stars, gas, and dust. As the galaxies emerge from the first passage, moving apart after having punched through each other, they'll trail long tidal tails behind them. These tails form because the gravitational force from the other galaxy is stronger on the near side of each system than on the far side, creating tidal forces that stretch each galaxy along the line connecting their centers. Stars and gas on the outer edges of each galaxy, where the binding is weakest, are pulled away from the main bodies and left behind in streams that follow the galaxy's orbital trajectories. These tidal tails can extend for hundreds of thousands or even millions of light years, creating spectacular structures visible to distant observers. Some of the most beautiful images of colliding galaxies captured by the Hubble Space Telescope show these tidal features, long, graceful arcs of stars and gas stretching across intergalactic space. The antennae galaxies, currently undergoing a merger similar to what the Milky Way and Andromeda will experience, show tidal tails extending more than 300,000 light-years from the main bodies, remnants of stars ejected during their collision. After the first passage, the two galaxies will separate, moving perhaps 500,000 light-years apart before their mutual gravitational attraction slows their recession and pulls them back together for a second collision. This turnaround phase takes roughly 500 million to a billion years, depending on the exact parameters of the first encounter. During this respite, both galaxies will attempt to relax back toward equilibrium, but they'll be fundamentally changed from their pre-collision configurations. The second collision, occurring perhaps 500 million years after the first, will be more violent than the initial encounter. More stars have been scattered into extended distributions by the first passage, creating larger cross-sections for gravitational interactions during the second pass. More gas has been disturbed and displaced, setting up additional collision zones where gas clouds from the two galaxies will compress and trigger new starbursts. Each passage removes orbital energy from the system through a process called dynamical friction, where gravitational interactions with individual stars extract momentum from the galaxy's relative motion. Think of it as gravitational drag. As the galaxies pass through each other, they gravitationally interact with millions of stars, and those interactions preferentially remove energy from their orbital motion, causing subsequent passages to penetrate deeper and separate less after each encounter. By the third or fourth passage, the two galaxies will no longer have enough relative velocity to fully separate. Instead, they'll settle into a bound configuration, a single gravitationally bound system containing the stars, gas, and dark matter from both original galaxies. This doesn't mean the merger is complete. The newly bound system will be far from equilibrium, with stars and gas moving on chaotic orbits that reflect their complex gravitational history. But it does mean the systems can no longer escape each other. They're committed to eventual merger. The complete relaxation of this bound system into an equilibrium configuration takes several billion additional years. During this time, gravitational interactions between stars slowly redistribute energy and angular momentum, a process called violent relaxation that transforms the chaotic post-merger state into a more organized structure. The final product, emerging perhaps 2 to 3 billion years after the initial collision, will be a giant elliptical galaxy containing roughly 1 trillion stars, all the stars from both the Milky Way and Andromeda combined into a single system. This new galaxy, informally called Milkomeda or Milkdromeda by astronomers, will be fundamentally different from either progenitor galaxy. Instead of thin rotating disks with well-defined spiral structure, Milkomeda will be a three-dimensional ellipsoidal system where stars orbit in random directions. Some stars will orbit prograde, following the original rotation direction of the Milky Way. Others will orbit retrograde, having inherited the rotation of Andromeda, which approaches the Milky Way at an angle. Still others will orbit on highly elliptical trajectories that take them from the outer regions to the core and back. The night sky visible from any surviving planet in Milkomeda will be unrecognizable compared to our current view. Instead of the Milky Way's band of light stretching across the sky, observers would see a more uniform distribution of stars in all directions, the spheroidal structure of an elliptical galaxy providing a more isotropic view. The stellar density visible in the night sky would be higher on average. Milkomeda will contain more stars than the current Milky Way, but without the concentration into a thin disk, the distribution would be more uniform. But before the merger reaches this quiet endpoint, one more catastrophe must unfold. The central supermassive black holes, Sagittarius, a star from the Milky Way, and M31 star from Andromeda, must spiral together and merge, and that process will unleash some of the most violent physics the universe can produce. 45-minute hook point, word count, 32,200. The death of galaxies is written in the behavior of their central black holes. Every large galaxy contains a supermassive black hole at its core, and when galaxies collide, these black holes are destined to merge in events so violent they shake the fabric of space-time itself. The merger of Sagittarius A star and M31 star will represent one of the most energetic events in the history of our cosmic neighbourhood. An apocalypse measured not in the destruction of planets or stars, but in the warping of reality itself. When the Milky Way and Andromeda first collide, their central black holes will be separated by millions of light years, too far apart to directly interact. Each black hole sits at the gravitational centre of its galaxy, surrounded by dense concentrations of stars, gas, and dark matter that orbit in complex patterns determined by billions of years of galactic evolution. These black holes won't immediately respond to each other's presence. Their gravitational influence, while profound on galactic scales, is localized to the central regions of each galaxy. But as the galaxies pass through each other repeatedly, exchanging energy and angular momentum through gravitational interactions, the black holes trace out complex trajectories through the merging system. During each passage, they swing past each other at distances of hundreds of thousands of light years, each passage bringing them slightly closer as orbital energy is dissipated through dynamical friction. M31 star, Andromeda's central black hole, is roughly 25 times more massive than Sagittarius A star, containing approximately 100 million solar masses, compared to Sagittarius A star's 4 million solar masses. This mass difference means M31 star will dominate the gravitational dynamics of the merger, with Sagittarius A star effectively orbiting the more massive black hole as the two spiral together. The process of bringing the black holes from galactic scale separations, measured in hundreds of thousands of light years down to close binaries measured in light years, takes billions of years and involves several distinct physical mechanisms. The first stage, covering the reduction from millions of light years to thousands of light years, operates through dynamical friction at the galactic scale. The black holes drag against the background of stars and dark matter as they move through the merging galaxies, creating slight overdensities of matter in their wakes that gravitationally pull back on them, extracting orbital energy. This process is slow but inexorable. Each orbit through the merged galaxy removes a small fraction of the black hole's kinetic energy, causing their orbits to decay. Over hundreds of millions of years, the separation decreases from the galactic scale to the scale of the central bulge, bringing the black holes to within a few thousand light years of each other. At this point, a second mechanism takes over. The black holes are now deep within the dense stellar environment of the merged galactic core, surrounded by billions of stars packed into a relatively small volume. As the black holes orbit each other at this reduced separation, they gravitationally interact with stars that pass nearby, scattering those stars to higher velocities and absorbing their orbital energy in exchange. Think of this as gravitational three-body scattering. When a star approaches the binary black hole system, it interacts gravitationally with both black holes. If the encounter is arranged correctly, the star can gain energy from the binary's orbital motion, being flung away at high velocity, while the binary loses an equivalent amount of energy and shrinks its separation. This process ejects stars from the galactic core at hundreds of kilometers per second, creating a population of hypervelocity stars while slowly bringing the black holes closer together. This mechanism works efficiently down to separations of about 1 light year, at which point a problem emerges. The core of the merged galaxy becomes depleted of stars in the immediate vicinity of the binary black hole. Most stars that were on orbits that brought them close enough to interact with the binary have already been scattered away. The remaining stars in the core orbit on trajectories that don't bring them close enough for efficient energy transfer. The binary black hole system can stall at this separation, trapped in what astronomers call the final parsec problem. For years, this final parsec problem puzzled theorists studying galaxy mergers. How do supermassive black hole binaries bridge the final gap from light-year separations to the milliparsec separations where gravitational wave emission becomes strong enough to drive merger on reasonable timescales? Several solutions have been proposed, and the real answer probably involves a combination of mechanisms. Gas inflow provides one solution, If the merged galaxy contains significant amounts of gas in its central regions, that gas can form an accretion disk around the binary black hole system. As gas spirals inward, it exerts torques on the black holes, transferring angular momentum from the binary to the gas. The gas carries away this angular momentum through turbulent processes and magnetic fields, while the binary loses angular momentum and shrinks its separation. This mechanism can be quite efficient if enough gas is present, potentially solving the final parsec problem entirely. The Milky Way Andromeda merger will likely provide plenty of gas for this process. Both galaxies contain substantial gas reservoirs in their disks, and the collision will drive gas inflows toward the merged galactic core through gravitational torques. Conservative. Estimates suggest tens of millions to hundreds of millions of solar masses of gas could accumulate in the central kiloparsec of Milkomeda, more than enough to fuel the black hole merger and power intense episodes of active galactic nucleus activity. A second mechanism involves non-axisymmetric structure in the stellar distribution. If the merged galactic core is not perfectly spherical, but instead has some elongation or triaxiality, stars on certain orbits can resonantly interact with the binary black holes, enabling continued energy transfer even after the core is mostly depleted. Numerical simulations suggest this can reduce the stalling timescale substantially, though whether it completely solves the final parsec problem remains debated. Ultimately, once the binary black holes reach separations of about 1/10 of a light year, a new physical mechanism dominates the merger dynamics. Gravitational waves, ripples in space-time predicted by Einstein's general relativity, carry away energy and angular momentum from the orbiting black holes. At large separations, this energy loss is negligible. But as the black holes spiral closer, the gravitational wave emission increases dramatically, eventually becoming the dominant mechanism for orbital decay. The gravitational wave luminosity scales with the 5th power of the orbital frequency, meaning as the black holes orbit faster, they radiate gravitational waves at exponentially increasing rates. At a separation of 1/10 of a light year, they're orbiting each other roughly once every 1,000 years, and the gravitational wave emission is barely measurable. But as they spiral inward, the orbital period decreases and the gravitational wave power increases. At a separation of 1 light month, they're orbiting roughly once per year, and the gravitational waves are carrying away the equivalent of several solar masses of energy per million years. At 1 light week, the orbital period is measured in weeks, and the energy loss exceeds the total luminosity of a bright galaxy. At 1 light day, they're orbiting every few days, and the gravitational waves are so powerful they'd be easily detectable by space-based gravitational wave observatories anywhere in the galaxy. The final months before merger become a runaway process. As the black holes spiral closer, they orbit faster, emit stronger gravitational waves, lose more energy, spiral closer still, accelerating the process. The orbital period shrinks from days to hours to minutes. The gravitational wave frequency increases from millihertz to hertz to hundreds of hertz. The space-time curvature around the black holes becomes so extreme that the fabric of space and time itself begins to exhibit non-linear dynamics, effects beyond the predictions of simple general relativity. In the final hours before merger, the two event horizons approach each other at substantial fractions of the speed of light. The space-time around each black hole is already curved so severely that light cannot escape. But now the two regions of extreme curvature are approaching, about to overlap and create an even more extreme gravitational environment. The black holes are not just orbiting in curved space-time, they're orbiting through space-time that's churning, twisting, being dragged along by their rotation in relativistic frame-dragging effects. The final moments last only seconds. The black holes complete their last few orbits in a blur of relativistic motion, whipping around each other at speeds approaching the speed of light. Their event horizons stretched and deformed by tidal forces and extreme rotation. The gravitational waves they emit reach peak amplitudes and frequencies in the hundreds of hertz range, carrying away 3 solar masses worth of energy in the final second before merger. Then the event horizons touch. The 2 black holes become one, their horizons merging into a single distorted event horizon that quickly settles into the characteristic shape of a rotating black hole. But the merger doesn't happen quietly. The asymmetric emission of gravitational waves during the final orbits and merger creates a net momentum, a recoil velocity that kicks the merged black hole away from its initial position. This gravitational recoil, sometimes called a gravitational wave kick, results from conservation of momentum. When gravitational waves are emitted preferentially in certain directions due to asymmetries in the merger, the black hole recoils in the opposite direction like a rocket. The magnitude of this recoil depends sensitively on the mass ratio, spin magnitudes, and spin orientations of the merging black holes. For the Sagittarius A star and M31 star merger, with a mass ratio of roughly 25:1 and unknown spin configurations, recoil velocities could range from tens to potentially thousands of kilometers per second. Conservative estimates suggest several hundred kilometers per second is most likely, enough to displace the merged black hole significantly from the center of Milkomeda, but probably not enough to eject it from the galaxy entirely. This means that for millions of years after the black hole merger, Milkomeda will have an off-center supermassive black hole oscillating back and forth through the galactic core as it slowly settles back toward the gravitational center through dynamical friction. During this time, the gravitational potential in the central regions will be disturbed, affecting stellar orbits throughout the inner galaxy and potentially triggering unusual dynamical effects in the nuclear stellar population. But the gravitational wave emission itself represents the most dramatic signal from the merger. For those final seconds before the black holes merge, they're emitting gravitational waves with peak luminosity exceeding the electromagnetic luminosity of every star in the observable universe combined. 3 solar masses worth of energy, converted to pure gravitational radiation in the final second. This is the brightest gravitational wave source in cosmic history for our galactic neighbourhood, an event that won't be repeated until the next major galaxy merger occurs billions of years in the future. The gravitational waves propagate outward from the merger at the speed of light, rippling through space-time and carrying information about the black hole, masses, spins, and orbital dynamics. When they reach Earth, or wherever Earth happens to be located 4 billion years from now, they'll cause measurable distortions in the distances between objects as the waves alternately compress and stretch space-time. These distortions are tiny, even for a merger as energetic as the Sagittarius A star and M31 star collision. The gravitational wave strain measured at Earth would be approximately 10 to the power of 17, meaning objects would be displaced by 1 part in 100 million billion of their separation. A 1-meter rod would be stretched and compressed by about 10 to the power of 17 meters, roughly 1,000th the diameter of a proton. But this strain is detectable by sufficiently sensitive instruments. Current ground-based gravitational wave detectors like LIGO are sensitive to strains around 10 to the power of 21 for brief signals from stellar mass black hole mergers. Space-based observatories under development, like LISA, are designed to detect lower frequency gravitational waves from supermassive black hole mergers at strains around 10 to the power of 20. The Sagittarius A star and M31 star merger would be easily detectable by such instruments, producing a signal lasting several months as the black holes spiral together from separations where LISA is sensitive down to the final merger. Any civilization in the Milky Way or Andromeda with technology capable of detecting gravitational waves will have months of advance warning before the final merger occurs. They'll be able to watch the signal strengthen as the black holes spiral closer, measuring the increasing frequency and amplitude of the gravitational waves and using that information to predict exactly when the merger will occur. This would be one of the few cosmic catastrophes that's completely predictable. the gravitational wave signal providing a countdown clock to the moment when reality itself is restructured at the galactic core. The merger of the central black holes marks a transition point in the life of the combined galaxy. Before the merger, Milkomeda consists of two populations of stars with distinct dynamical histories, stars from the Milky Way and stars from Andromeda, mixing but still somewhat segregated by their different orbital properties. After the merger, with a single central black hole replacing the two original monsters, the galaxy has one gravitational center and one unified destiny. The transformation from two galaxies to one is complete at that moment, even though the stellar populations will continue mixing and relaxing for billions of additional years. And throughout this entire process, another form of cosmic violence has been unfolding invisibly. The dark matter halos of both galaxies have been colliding, passing through each other, and creating gravitational chaos that operates completely beyond our ability to observe directly. This is the hidden apocalypse, the dark matter catastrophe that accompanies every galaxy merger. Word count: 38,500. Dark matter doesn't collide the way normal matter does. When gas clouds from two galaxies crash together, the atoms collide, creating heat, pressure, shock waves, all the phenomena are associated with fluid dynamics. Dark matter, whatever it's made of, doesn't interact through electromagnetic forces. It can't heat up or create pressure waves. When dark matter distributions from two galaxies interpenetrate, the dark matter particles pass right through each other, experiencing only gravitational forces. But those gravitational forces are profound. Dark matter makes up approximately 85% of the matter in each galaxy. So when two dark matter halos collide, the majority of each galaxy's mass is participating in a purely gravitational interaction. And that interaction reshapes the entire gravitational potential of the merged system in ways that profoundly affect the visible matter. When the Milky Way and Andromeda collide, their dark matter halos will pass through each other on the first encounter, just like the stellar disks. But unlike the stars, which are discrete objects that maintain their identities as they pass through, the dark matter forms continuous distributions that can develop complex structure during the collision. Computer simulations of dark matter halo collisions show that the interpenetrating halos develop wakes and trailing structures, regions of enhanced density where dark matter has been compressed by gravitational forces during the collision. These density enhancements create gravitational potential wells, regions where the gravitational field is stronger than average. When gas clouds from the visible matter move through these enhanced gravitational regions, they experience additional compression beyond what the collision with gas from the other galaxy would create. This can trigger star formation in locations where the visible matter alone wouldn't provide enough density for gravitational collapse. The dark matter collision also creates gravitational shocks, discontinuities in the gravitational field that propagate through both halos. These aren't shock waves in the traditional sense. They don't involve pressure or temperature, because dark matter doesn't have pressure or temperature. But they are regions where the gravitational potential changes rapidly over short distances, and these rapid changes can affect the dynamics of stars and gas clouds that happen to be passing through those regions when the shocks arrive. Perhaps most importantly, the dark matter collision determines the overall structure of the merged system. While the visible matter gets scattered and heated during the collision, losing orbital energy through gas collisions and stellar scattering, the dark matter evolves more conservatively, mixing while preserving more memory of its initial configuration. The final dark matter distribution in Milkomeda will reflect the orbital parameters and internal structures of both original galaxies' dark matter halos, creating a new halo that's more massive and more extended than either progenitor. This new dark matter halo will be roughly ellipsoidal rather than spherical, reflecting the merger geometry and the fact that the system won't have had time to fully relax into a spherical configuration by the time the merger is nominally complete. This ellipsoidal structure will persist for billions of years, slowly becoming more spherical as gravitational interactions redistribute energy and angular momentum throughout the halo. But the dark matter collision creates more than just structural changes. It also produces violence of a different kind, gravitational perturbations strong enough to tear apart satellite galaxies that happen to be in the wrong place at the wrong time. The dozens of dwarf galaxies that orbit the Milky Way and Andromeda as satellites will all experience extreme gravitational forces during the merger, and many won't survive intact. Small galaxies are held together by relatively weak gravitational binding. Their escape velocities are low enough that tidal forces from the merging giant galaxies can overcome the self-gravity of the dwarfs, pulling them apart and scattering their stars and dark matter throughout the merged system. Simulations suggest that at least half of the satellite galaxies in the local group will be tidally disrupted during the Milky Way-Andromeda collision, their stars added to the growing population of Milkomeda, while their dark matter halos are shredded and mixed into the merged dark matter distribution. This represents a hidden genocide, the deaths of dozens of galaxies that few people have ever heard of but which are nonetheless complete stellar systems in their own right. The large and small Magellanic Clouds, visible from Earth's southern hemisphere as fuzzy patches in the night sky, will likely be torn apart during the merger. The dozens of ultra-faint dwarf galaxies discovered in recent surveys, stellar systems containing only a few thousand stars each, but still gravitationally bound structures with their own identities, will be dissolved into the larger system. Each of these disruptions represents the end of a world, even if those worlds contained no planets and never harboured life. These satellite galaxies have existed for billions of years, evolving their own stellar populations, developing their own internal structures, orbiting the larger galaxies as independent objects. The merger will erase them, absorbing their stars and leaving behind only tidal streams and scattered remnants to mark where they once existed. The violence of this dark matter-driven destruction is completely invisible to electromagnetic observation. You can't see dark matter collision, can't photograph the gravitational shocks, can't measure the density enhancements directly. All the evidence comes from the effects on visible matter, stars being scattered in unexpected patterns, gas clouds compressing in regions where no visible mass is present, satellite galaxies being torn apart by tidal forces stronger than the visible matter alone could generate. This hidden violence represents a fundamental aspect of cosmic evolution that operates completely outside our direct sensory experience. The universe is filled with dark matter interactions that shape galactic evolution, but we can only detect these interactions indirectly through their gravitational effects on the small fraction of matter that does emit light. We're watching shadow puppets on a wall, inferring the shapes and motions of invisible objects from the shadows they cast on visible matter. And the shadow puppets tell a disturbing story. The universe on its larger scales is dominated by dark matter dynamics, by gravitational interactions between invisible structures that outweigh everything we can see by factors of 5 to 10. Galaxy evolution is driven primarily by dark matter merger history, with the visible stars and gas effectively along for the ride, responding to gravitational potentials determined by invisible matter distributions. When galaxies collide, the violence we can see is the stars being scattered, the gas clouds compressing and forming new stars, the spiral structures being destroyed. But the more massive violence is invisible, dark matter halos passing through each other, mixing, creating complex gravitational structures that will determine the shape and dynamics of the merged system for billions of years to come. We live in a universe where most of the action is invisible, where the fate of galaxies is written in the behaviour of matter we can detect only through its gravitational influence. The Milky Way-Andromeda collision will be no exception. The visible fireworks, the starburst regions and tidal tails and scattered stellar populations represent only a small fraction of the total violence. The majority of the action will be invisible, dark matter halos colliding and mixing, creating gravitational structures that shape the destiny of the merged system, but remain forever hidden from direct observation. And when the merger is complete, When Milkomeda has settled into its final configuration 6 or 7 billion years from now, the galaxy that emerges will be fundamentally different from either the Milky Way or Andromeda. Not just in its visible structure, the transformation from spiral to elliptical galaxy, but in its dark matter distribution, its gravitational potential, its dynamical properties. A new world formed from the deaths of 2 old ones. But the death of galaxies doesn't end with merger. It continues for trillions of years after merger, through slow processes that will eventually transform even Milkomeda into something cold, dark, and lifeless. The merger is just the beginning of a much longer story of galactic death. 60-minute hook point, word count, 45,500. The final fate of Milkomeda depends on cosmic evolution over timescales that dwarf the current age of the universe. The merger between the Milky Way and Andromeda will be complete in 6 to 7 billion years, producing a giant elliptical galaxy containing roughly 1 trillion stars. But that galaxy won't remain static. It will continue evolving through stellar evolution, dynamical processes, and the slow but inexorable expansion of the universe that will ultimately isolate it from most of the cosmos. The first major change will be the gradual dimming of the merged galaxy as its stellar population ages. Star formation will largely cease after the merger completes. The starburst phases during the collision will consume most of the available gas, converting it into new stars or driving it out of the galaxy through supernova-powered winds. What gas remains will be too hot or too dispersed to collapse and form new stars. Milkomeda will become what astronomers call a red and dead elliptical galaxy, containing mostly old stars with little ongoing star formation. The stellar population will be dominated by low-mass stars, red dwarfs containing less than half the Sun's mass that can burn hydrogen for trillions of years. More massive stars like the Sun and larger will have exhausted their fuel and died, transforming into white dwarfs, neutron stars, or black holes depending on their initial masses. The most massive stars, those containing dozens of solar masses, live only a few million years before exploding as supernovae. These stars will all be gone within a few tens of millions of years after the merger completes. Sun-like stars live roughly 10 billion years. The Sun itself, currently 4.6 billion years old, will die in about 5 billion years, roughly 1 billion years after the Milky Way Andromeda collision begins. Most of the Sun-like stars in Milkomeda will have died by about 15 billion years after the Big Bang, leaving behind white dwarfs, dense stellar cores roughly the size of Earth containing about half to a full solar mass compressed into Earth-sized volumes. But the lowest mass stars, red dwarfs containing 10 to 50% of the Sun's mass, live for trillions of years. These stars burn hydrogen so slowly that the least massive red dwarfs currently existing won't die for thousands of times the current age of the universe. They'll be the last stars shining in Milkomeda, dim red embers that persist long after everything else has gone dark. Over timescales of hundreds of billions to trillions of years, the stellar population will transition from the relatively bright mix of stars visible today to a much dimmer population dominated by red dwarfs and stellar remnants. The galaxy's luminosity will decrease continuously as stars die and are not replaced by new star formation. Eventually, perhaps 1 trillion years from now, Milkomeda will contain mostly stellar remnants, white dwarfs, neutron stars and black holes, with only a small population of the longest-lived red dwarf still burning hydrogen. But stellar evolution represents only one process transforming the merged galaxy. Dynamical evolution, the gradual rearrangement of stellar orbits through gravitational interactions, continues operating over these same ultra-long timescales. Stars occasionally pass close to each other, exchanging energy and angular momentum through gravitational encounters. These encounters are rare for any given star, occurring perhaps once every trillion years on average. But in a galaxy containing 1 trillion stars, they happen millions of times per year statistically. Each encounter slightly changes the orbits of the participating stars, some gaining energy and moving to larger radii, others losing energy and sinking toward the galactic core. Over immensely long timescales, these encounters cause the galaxy to evolve through a process called evaporation. Stars that gain enough energy through gravitational encounters can exceed the galaxy's escape velocity and leave the system entirely, becoming intergalactic wanderers travelling through the void between galaxies. Simultaneously, stars that lose energy sink toward the galactic core, building up the central density. This creates a positive feedback effect where the higher central density leads to more frequent encounters, which causes more energy redistribution, leading to more evaporation and more core condensation. Eventually, this process can lead to core collapse, where the central density becomes so high that stellar dynamics become dominated by frequent encounters and eventual formation of a dense stellar nucleus. But before core collapse occurs, another process becomes important. The central supermassive black hole, containing roughly 100 million solar masses after the merger of Sagittarius A star and M31 star, will continue growing through occasional captures of stars that wander too close. Each star that falls into the black hole adds its mass to the black hole, slowly but steadily increasing the monster's size. Over trillions of years, a substantial fraction of Milkomeda's stellar population could be consumed by the central black hole through this process. Stars that pass within a few gravitational radii of the black hole can be captured through tidal forces or direct in spiral. The fraction of stars ultimately captured depends on the galaxy's density profile and how efficiently gravitational encounters can deliver stars to the black hole's vicinity. Estimates suggest that perhaps 10 to 30% of Milkomeda's stars could eventually be consumed by the central black hole over timescales of 10 to 100 trillion years. This represents a slow but steady process of galactic cannibalism where the black hole literally eats the galaxy from the inside out, growing to perhaps several hundred million or even a billion solar masses by consuming the surrounding stellar population. But even this vast timescale is dwarfed by the ultimate fate awaiting all matter in the universe. On timescales approaching a googol years, 10 to the power of 100 years, unimaginably longer than any timescale mentioned so far, even stable matter begins to decay through processes predicted by particle physics, but never observed because they operate over timescales billions of times longer than the current age of the universe. Protons, the hydrogen nuclei that make up most of normal matter, might be unstable on these ultra-long timescales. Some grand unified theories predict proton decay with half-lives around 10 to the power of 34 to 10 to the power of 36 years. If protons decay, then all normal matter eventually disintegrates into lighter particles, photons, and neutrinos. White dwarfs, which are mostly composed of carbon and oxygen nuclei surrounded by degenerate electron gases, would evaporate as their constituent protons decay. Neutron stars containing degenerate neutron matter would similarly decay into lighter particles. Even black holes aren't eternal. Stephen Hawking predicted that black holes evaporate through quantum mechanical processes, slowly radiating away their mass as thermal radiation. The evaporation timescale depends on the black hole's mass, with more massive black holes taking longer to evaporate. For a solar mass black hole, the evaporation timescale is roughly 10 to the power of 67 years. For Milkomeda's central black hole, containing hundreds of millions of solar masses, the evaporation timescale extends to approximately 10 to the power of 98 years. On these incomprehensible timescales, the universe transforms into something completely alien to our experience. All the stars have died. All the stellar remnants have either fallen into black holes or evaporated through proton decay. The black holes themselves are slowly evaporating, emitting Hawking radiation that carries away their mass over timescales that make the age of the universe seem like an eye blink. Eventually, in the unimaginably distant future, when the universe is perhaps 10 to the power of 100 years old, roughly a googol years, even the black holes will have evaporated. What remains will be a thin soup of photons, neutrinos, and perhaps some exotic particles like dark matter if dark matter is stable on these timescales. The temperature will be infinitesimally close to absolute zero, the density will be vanishingly small, and everything that once was Milkomeda, all trillion stars, the supermassive black hole, the dark matter halo, everything, will have been transformed into an incredibly diffuse cloud of fundamental particles spreading through an ever-expanding universe. This is the ultimate fate of galaxies, not dramatic explosions or catastrophic collisions, though those certainly occur along the way, but a slow fading into darkness and dissolution that takes longer than human minds can comprehend. The merger of the Milky Way and Andromeda represents one chapter in this incomprehensibly long story, a brief period of violence and restructuring that will seem infinitesimal when viewed from the perspective of the universe's ultimate fate. But for observers living through the merger, for any hypothetical civilizations existing in either galaxy during the collision, the merger will be the defining cosmic event of their existence. The sky will change beyond recognition. The galactic environment will be transformed. The stable conditions that allowed life to develop and civilizations to rise will be disrupted by forces beyond any possibility of control. And through it all, the dying will have been inexorable. The galaxies were doomed from the moment they formed, gravitationally bound in a cosmic dance that could only end in merger. No technology, no matter how advanced, could prevent the collision. No amount of warning, no matter how far in advance, could change the outcome. The death of these galaxies was written into the laws of physics billions of years before the first life arose on Earth. This is the Cosmic Catastrophe Protocol, the universe's algorithm for killing galaxies and recycling their matter into new structures, and it's happening all around us throughout the universe, in every corner of the cosmos where galaxies orbit close enough to eventually collide. The Milky Way's death is inevitable. The only question is what happens afterward. And that story, the story of Milkomeda's slow fade into darkness, will be told over trillions of years by the cooling remnants of stars that once illuminated two proud spiral galaxies. Part 3. The Fires of Creation. The collision will transform both galaxies into stellar foundries operating at scales and intensities never seen during their peaceful spiral phase. When gas clouds from the Milky Way and Andromeda collide at hundreds of kilometers per second, they won't simply bounce off each other or merge smoothly. They'll compress, heat, and trigger the most violent episode of star formation either galaxy has experienced in billions of years. This is the starburst phase, and it will reshape the galactic landscape through fire. Star formation under normal conditions is a relatively sedate process. Cold molecular clouds in galactic disks gradually accumulate mass through gravitational attraction. When regions within these clouds reach critical densities, roughly 100,000 hydrogen molecules per cubic centimetre, they begin to collapse under their own gravity. The collapse heats the interior until temperatures reach 10 million degrees, hot enough for hydrogen fusion to ignite. A new star is born. This process typically takes millions of years from the initial collapse to the moment the star begins burning hydrogen. And in a stable spiral galaxy like the current Milky Way, star formation proceeds at a steady pace, converting roughly 1 to 3 solar masses of gas into new stars each year. Over billions of years, this adds up to substantial stellar populations, but at any given moment the star formation rate is modest. Galaxy collisions change everything. When two galaxies' interstellar media collide, gas clouds crash together at relative velocities of hundreds of kilometers per second. These aren't gentle encounters. The kinetic energy of collision converts to thermal energy, heating the gas to millions of degrees, but paradoxically, this heating is exactly what triggers massive star formation. Here's why. When diffuse gas clouds collide, the collision creates shockwaves that propagate through both clouds. Behind these shock fronts, the gas compresses dramatically, increasing the density by factors of 10 to 100. Higher density means stronger gravitational attraction between gas particles. Regions that were too diffuse to collapse under their own gravity suddenly find themselves dense enough for gravitational collapse to begin. But there's a second crucial effect. The shocks also drive turbulence in the gas, creating chaotic motions that mix and compress the material on multiple scales. This turbulence fragments the gas clouds into thousands of smaller clumps, each massive enough to form stars. Instead of a few isolated regions collapsing to form stars over millions of years, the entire collision zone lights up with star formation occurring simultaneously across vast regions. The result is a starburst, an episode where the star formation rate increases by factors of 10 to 100 compared to normal conditions. During peak starburst phases of the Milky Way Andromeda collision, the combined system might form hundreds of solar masses worth of new stars each year, converting gas into stars at rates not seen in either galaxy for billions of years. These newborn stars aren't evenly distributed across the mass spectrum. Star formation physics naturally produces what astronomers call an initial mass function, a distribution of stellar masses that favours low-mass stars over high-mass stars. For every star containing 10 solar masses, roughly 10 stars containing one solar mass form, and roughly 100 stars containing 1/10 of a solar mass. But during intense starburst events, this mass distribution can shift toward more massive stars. The high-density, high-temperature conditions in collision zones favour the formation of massive stars, those containing 20 to 100 solar masses or even more. These stellar monsters burn hydrogen at prodigious rates, producing luminosities thousands to millions of times greater than the Sun. A star containing 100 solar masses, at the extreme end of what's physically possible, can have a luminosity 5 million times greater than the Sun. It burns so hot that its surface temperature exceeds 50,000 Kelvin, more than 8 times hotter than the Sun's surface. The star emits most of its light in the ultraviolet part of the spectrum, radiation so energetic it ionizes hydrogen gas across thousands of light years. These massive stars dominate the appearance of starburst regions despite being relatively rare numerically. A starburst cluster might contain thousands of stars, but the handful of most massive stars produce more light than all the others combined. When astronomers photograph starburst galaxies, what they're seeing is primarily the light from these stellar giants, young, hot, and incredibly luminous stars that burn through their hydrogen fuel in only a few million years. The ultraviolet radiation from massive stars has profound effects on the surrounding environment. When high-energy photons strike hydrogen atoms in nearby gas clouds, they knock electrons free, ionizing the gas and creating what astronomers call Xi regions, volumes of ionized hydrogen that glow with characteristic red light as electrons recombine with protons. These emission nebulae can span hundreds of light years, vast glowing bubbles surrounding star clusters. The famous Orion Nebula, visible to the naked eye in Earth's night sky as a fuzzy patch in the constellation Orion, is an HII region powered by a cluster of young, massive stars. The nebula spans about 25 light years and shines with the red light of hydrogen emission. But it's relatively small and dim compared to the giant HI regions that will form during the Milky Way Andromeda collision. The collision zones will create HI regions spanning thousands of light years, vast bubbles of ionized gas glowing so brightly they'll be visible from other galaxies. These supergiant HI regions, sometimes called HI galaxies when they're large enough to dominate their host galaxy's appearance, represent some of the most spectacular cosmic structures produced during galaxy mergers. But ultraviolet radiation is only one way massive stars affect their environments. These stars also produce powerful stellar winds, streams of charged particles blown off their surfaces by radiation pressure. A massive star can lose the equivalent of Earth's mass every year through stellar winds, expelling material at velocities of thousands of kilometers per second. These winds collide with the surrounding interstellar medium, creating wind-blown bubbles that expand through space like invisible bulldozers. The fastest stellar winds can create superbubbles, cavities in the interstellar medium spanning hundreds of light years. When multiple massive stars form in the same region, their combined winds can excavate enormous volumes, creating Swiss cheese-like structures in the galactic disk. The Milky Way currently contains several superbubbles created by stellar winds from massive star clusters. The local bubble, a cavity roughly 300 light-years across, centered approximately on the Sun's current location, was excavated by supernova explosions and stellar winds from a moving group of massive stars that passed through this region several million years ago. We're living inside a cavity created by stellar violence. During the starburst phases of the merger, superbubbles will form throughout both galaxies, creating vast interconnected cavities that fundamentally alter the structure of the interstellar medium. Gas will be compressed into shells surrounding the bubbles, creating dense regions that might trigger additional star formation in a positive feedback cycle. But simultaneously, the expanding bubbles will heat gas to temperatures too high for star formation, creating regions where the star formation process is suppressed. This interplay between triggered star formation and feedback-driven suppression represents one of the most complex aspects of galaxy evolution. Simulating these processes requires tracking the behavior of gas on scales ranging from individual stars to entire galaxies, spanning 10 orders of magnitude in size. Modern supercomputer simulations struggle to capture all the relevant physics, but they agree on the broad outlines of what happens during merger-driven starbursts. The starburst peaks during and shortly after each close passage between the galaxies. As the disks interpenetrate, compression is maximal, triggering intense star formation across the collision zones. But the starburst continues even after the galaxies separate, as gravitational perturbations drive gas inflows toward the galactic centers, feeding additional star formation in the inner regions. Between passages, during the hundreds of millions of years when the galaxies are separating before falling back together, the star formation rate decreases somewhat, but remains elevated compared to pre-collision levels. The tidal disturbances have fundamentally altered the gas distribution in both galaxies, creating instabilities that continue driving gas collapse and star formation even without ongoing collisions. By the time the merger completes, a Milkomeda settles into its final configuration. Perhaps 70 to 80% of the pre-collision gas supply will have been converted into stars or expelled from the galaxy entirely. The remaining gas will be too hot, too dispersed, or too metal-enriched to efficiently form new stars. Milkomeda will transition from a star-forming system to a quiescent elliptical galaxy, red and dead, containing mostly old stars with little ongoing star formation. But before that quiet endpoint is reached, the starburst phase will create spectacular fireworks, and the most dramatic fireworks of all come when massive stars die. 75-minute hook point. Word count 52,300. Massive stars live fast and die young. A star containing 100 solar masses exhausts its hydrogen fuel in roughly 3 million years, less than 1,000th the Sun's 10 billion year lifetime. When the hydrogen is gone, the star doesn't simply fade away. It begins fusing heavier elements, working its way up the periodic table in a desperate attempt to maintain the radiation pressure that keeps gravity from crushing the star's core. Hydrogen fuses to form helium. Helium fuses to form carbon and oxygen. Carbon fuses to form neon and magnesium. Oxygen fuses to form silicon and sulfur. And finally, silicon fuses to form iron. Each fusion stage produces less energy than the previous one and burns through fuel faster. The star is accelerating toward its doom, exhausting each successive fuel source in shorter and shorter periods. The final stages proceed with terrifying rapidity. Silicon burning, the last fusion stage before the star runs out of options, lasts only a few days. During this time, the star's core transforms into a ball of iron roughly the size of Earth. containing about 1.5 times the Sun's mass. Iron nuclei are the most tightly bound atomic nuclei in nature. Fusing iron into heavier elements requires energy input rather than releasing energy. The fusion production line has reached its absolute end. With no more fusion to generate outward pressure, the iron core becomes unstable. Gravity, which has been held at bay for millions of years by radiation pressure, finally wins. The core collapses. The collapse happens fast. In less than 1 second, the Earth-sized iron core compresses to a sphere roughly 10 kilometers in radius, shrinking by a factor of 1,000 in linear dimension and 1 billion in volume. The density increases to nuclear densities, roughly 400 million tons per cubic centimeter. A sugar cube-sized chunk of core material would outweigh all of humanity combined. This is matter, in a state that doesn't exist anywhere else in the universe except neutron stars and the cores of collapsing supernova. Atomic nuclei are crushed so tightly together that electrons are forced to merge with protons, converting them into neutrons through weak nuclear interactions. The core becomes a ball of neutrons, a single atomic nucleus the size of a city, held together by the same nuclear forces that bind protons and neutrons in normal atomic nuclei. But this neutron core is incompressible. When the infalling matter crashes into the neutron surface, it rebounds violently, launching a shock wave that propagates outward through the still collapsing outer layers of the star. This rebound shock carries enormous energy, roughly 10 to the 53 ergs, equivalent to the gravitational binding energy of the neutron star. To put this in perspective, that's roughly 100 times the total energy the Sun will radiate over its entire 10 billion year lifetime, released in less than 10 seconds. The shock wave blasts through the star's outer layers, heating them to billions of degrees and accelerating them to velocities exceeding 10% of the speed of light. As the shock propagates, it encounters the various shells of material synthesized during the star's life, regions rich in oxygen, silicon, carbon, helium. The extreme temperatures and densities in the shock reactivate fusion reactions, creating new elements through explosive nuclear synthesis. Elements heavier than iron, those that cannot form through normal stellar fusion because they require energy input, are synthesized in the shock-heated layers during the brief seconds the supernova shock is passing through. Neutrons released during the core collapse are captured by atomic nuclei in a rapid chain of captures and radioactive decays, building up heavier and heavier elements through what's called the R process, rapid neutron capture. Gold, platinum, uranium, all the elements heavier than iron owe their existence to this process. The supernova shock creates conditions that don't exist anywhere else, high enough neutron densities and temperatures to build up heavy elements through successive neutron captures occurring faster than the newly created nuclei can decay. In a few seconds of explosive violence, the star forges elements that will persist for billions of years in the universe's inventory of matter. Then the outer layers explode, blasting into space at thousands of kilometers per second. The supernova brightens over a few hours to reach peak luminosity, shining with the light of billions of normal stars. For a brief period, a single exploding star can outshine an entire galaxy. The light comes primarily from radioactive decay of nickel-56, synthesized in the explosion, which decays through cobalt-56 to iron-56 over a few months, releasing gamma rays that heat the expanding debris and cause it to glow. From Earth's perspective, if Earth witnesses any of these explosions during the merger, supernova will appear as new stars in the sky, brightening over days to become easily visible to the naked eye before fading over months. If any supernova occurs within a few thousand light years, it could briefly become the brightest object in the night sky aside from the moon, casting shadows and visible during daytime. The Milky Way currently experiences roughly 2 to 3 supernovae per century, a rate determined by the galaxy's star formation history and the lifetimes of massive stars. During the starburst phase of the merger, with star formation rates increased by factors of 10 to 100, the supernova rate will increase proportionally. Instead of 2 or 3 supernovae per century, Milkomeda might experience dozens or even hundreds per century during peak starburst phases. This represents a dramatic increase in cosmic violence. Each supernova releases approximately 10 to the 51 ergs of kinetic energy into the surrounding interstellar medium, enough to excavate a bubble hundreds of light years across and heat the gas to millions of degrees. Multiple supernovae occurring in the same region within a few million years can create superbubbles spanning thousands of light years, vast cavities blown in the galactic disk by the cumulative effects of stellar explosions. The Carina Nebula, visible from Earth's southern hemisphere, shows what multiple supernovae can do to a star-forming region. This giant emission nebula spans roughly 300 light-years and contains several stellar clusters, including some of the most massive stars known. Over the past few million years, multiple supernovae have exploded in this region, creating a complex structure of bubbles, shells, and pillars carved from the original molecular cloud. During the merger, structures like the Carina Nebula will be common throughout both galaxies. Vast regions spanning thousands of light-years will glow with the light of H-I emission, carved into complex shapes by stellar winds and supernova shocks. New stars will continue forming in the compressed shells surrounding the superbubbles, maintaining the cycle of star formation even as previous generations of stars destroy the environments they were born in. But the increase in supernova rate has consequences beyond the spectacular visual fireworks. Supernovae also produce dangerous radiation. Each explosion emits intense bursts of X-rays, gamma rays, and cosmic rays, high-energy particles accelerated to near-light speed by the supernova shock. These particles can travel through the galaxy for millions of years, gradually losing energy through interactions with magnetic fields and interstellar gas. The cosmic ray background throughout the galaxy will increase substantially during the starburst phases. Planets in both galaxies will be bathed in higher levels of cosmic ray radiation than they experienced during the pre-collision period. For worlds with thick atmospheres like Earth, the atmosphere provides substantial shielding, absorbing most cosmic rays before they reach the surface. But the increased flux will still enhance the radiation dose at high altitudes and in space. More importantly, very close supernovae, those occurring within 30 light-years of a planetary system, can directly damage planetary atmospheres. The intense X-ray and gamma-ray burst from a nearby supernova can ionize upper atmospheric layers, triggering chemical reactions that destroy ozone molecules. On Earth, the ozone layer in the stratosphere absorbs most incoming ultraviolet radiation from the Sun. Without this protective shield, surface life would be exposed to dangerous levels of UV radiation that can damage DNA and proteins. A supernova within 10 light-years could temporarily reduce Earth's ozone layer by 50% or more, allowing dangerous UV radiation to reach the surface for years or decades until the ozone layer recovers. Mass extinction events in Earth's geological record show correlations with nearby supernova events, though the evidence is debated and alternative explanations exist for most extinction events. During the starburst phase of the merger, with supernova rates elevated by factors of 10 to 100, the probability of close supernova encounters increases proportionally. Any planetary system in a starburst region faces elevated risk of atmospheric damage from nearby supernovae. Life on such worlds would need to adapt to higher radiation levels, either through increased radiation resistance or by developing strategies to survive temporary collapses in atmospheric shielding. But radiation damage represents only one threat from the starburst environment. Another danger comes from the sheer number of massive stars forming in close proximity. These stars emit such intense ultraviolet radiation that they ionize surrounding gas across thousands of light-years, creating vast HI regions that are fundamentally hostile to planet formation and potentially to life. Young planetary systems require cold molecular gas to complete their formation. Planets form from disks of gas and dust surrounding newborn stars, and this material needs to remain relatively cool, a few hundred Kelvin, to allow dust grains to stick together and grow into planetesimals. But in starburst regions, the intense UV radiation from massive stars heats surrounding gas to tens of thousands of Kelvin, far too hot for planet formation to proceed normally. Planetary systems attempting to form in starburst regions might have their protoplanetary disks stripped away by UV radiation before planets can form. The intense photon flux heats the disk surface, creating thermal pressure that drives gas away from the star in a photoevaporation flow. Disks in starburst regions might survive only a few 100,000 years before being completely evaporated, too short for giant planets to form through core accretion. This suggests that starburst regions are essentially sterile from the perspective of planet formation, at least for the duration of the starburst. New stars can form, but they're unlikely to develop substantial planetary systems while they're bathed in the radiation from nearby massive stars. Only after the massive stars die, a few million years after formation, will conditions become calm enough for subsequent generations of stars to retain their protoplanetary disks long enough for planets to form. The implications for habitability are profound. Starburst regions, while spectacular and scientifically fascinating, are hostile environments for planet formation and potentially for life. Any hypothetical civilizations in either galaxy would want to avoid starburst regions, relocating to quieter parts of the galaxy where star formation proceeds at more sedate rates and the radiation environment is less extreme. But starburst regions don't last forever. They're transient phenomena, lasting a few tens of millions of years before the massive stars die and the elevated star formation rate declines. After the starburst ends, the region settles into a post-starburst phase, where star formation has largely ceased but many young stars remain. Stars that formed during the starburst but will live for billions of years. The Milky Way currently contains several post-starburst regions, areas where intense star formation occurred millions of years ago but has since declined. These regions contain unusually high concentrations of young stars but little ongoing star formation, a signature of past starburst activity. During and after the merger, much of Milkomeda will transition through starburst and post-starburst phases, creating a galaxy whose stellar population reflects its violent merger history. But perhaps the most important consequence of the starburst phase is chemical evolution. The massive stars that dominate starbursts are also the primary source of heavy elements in galaxies. When these stars explode as supernovae, they inject the elements synthesized during their lives and in their explosive deaths into the interstellar medium, enriching the gas with carbon, oxygen, silicon, iron, and heavier elements. This chemical enrichment affects all subsequent star formation. Stars that form from enriched gas have higher metallicities, more heavy elements mixed into their hydrogen and helium. These metallicities affect stellar properties, with higher metallicity stars having different opacities, burning rates, and evolutionary tracks compared to metal-poor stars. More importantly for life, chemical enrichment provides the raw materials for planet formation. Rocky planets like Earth are made primarily from heavy elements silicon, iron, magnesium, oxygen. These elements didn't exist when the universe was young. They were synthesized in stars and supernovae and returned to the interstellar medium through stellar winds and explosions. Each generation of stars that forms, lives and dies increases the metallicity of the remaining gas, enriching it with more heavy elements that will be incorporated into subsequent generations of stars and planets. The starburst during the Milky Way-Andromeda merger will dramatically accelerate chemical evolution in both galaxies. The elevated star formation rate means more massive stars, which means more supernovae, which means faster enrichment of the interstellar medium with heavy elements. Gas that forms stars after the starburst will have higher metallicity than gas-forming stars before the collision, a signature of the merger's influence on galactic chemical evolution that will persist for billions of years. By the time Milkomeda completes its transformation from two spiral galaxies into a single elliptical galaxy, its average stellar metallicity will be substantially higher than either progenitor galaxy before the collision. This chemical evolution represents one of the most important long-term consequences of the merger, changing the composition of the galaxy in ways that will affect every star and planet that forms in the post-merger galaxy. But the starburst represents only one aspect of how the merger transforms both galaxies. The gravitational interactions, the tidal forces, the repeated passages, all of these processes work together to destroy the beautiful spiral structures that characterize both galaxies before the collision and replace them with something entirely different. Word count: 59,000. The death of spiral structure happens gradually, a slow dissolution of the organized patterns that define spiral galaxies. Before the collision, both the Milky Way and Andromeda exhibit clear spiral arms, regions of enhanced stellar density that trace out logarithmic spirals from the galactic centers. These spiral arms aren't rigid structures, they're density waves, patterns maintained by gravitational resonances in rotating galactic disks. Here's how spiral density waves work. Stars in a galactic disk don't orbit at the same angular velocity. Stars closer to the galactic center orbit faster, completing their orbits in less time than stars farther out. This differential rotation should wind up any spiral pattern, causing it to become tighter and tighter until it disappears. But spiral arms persist for billions of years, maintaining their shapes despite the differential rotation that should destroy them. The solution to this winding problem involves understanding spiral arms not as material structures, but as density waves, regions where stars temporarily accumulate as they orbit. Think of it like a traffic jam on a highway. Cars enter the jam, slow down, become part of the dense region, then accelerate and leave the jam. The jam itself, the dense region, can remain stationary or move slowly even though the individual cars are constantly flowing through it. Spiral arms work similarly. Stars enter spiral arms as they orbit, spend some time in the denser region where they move more slowly due to the enhanced gravitational field, then leave the spiral arm and continue their orbits. The spiral pattern itself rotates at a different angular velocity than the individual stars, a pattern speed that's determined by the mass distribution and rotation curve of the galaxy. This delicate balance between differential rotation, gravitational forces, and the pattern speed of the spiral arms maintains spiral structure for billions of years in isolated galaxies. But galaxy mergers destroy this balance completely. When two galaxies collide, the gravitational field becomes asymmetric, dominated not by a single mass concentration at the center, but by the combined gravitational potential of both galaxies' mass distributions. During the first passage, as the galaxies interpenetrate, the spiral arms in both systems begin to distort. The gravitational pull from the other galaxy creates tidal forces that stretch the arms, pulling material away from the original spiral pattern. Stars that were following the density waves suddenly find themselves in a gravitational field that no longer supports the resonant orbits that maintain the spiral pattern. The arms begin to dissolve, transforming from graceful logarithmic spirals into more chaotic structures. Some regions become denser as tidal compression enhances the density waves locally. Other regions disperse as stars are pulled away from the spiral arms by the other galaxy's gravitational field. The overall pattern becomes less organized, less clearly defined. After the first passage, when the galaxies separate and move apart, both systems attempt to settle back toward equilibrium. New density wave patterns might form, temporary spiral structures that reflect the disturbed mass distribution. But these new patterns are less stable than the original spiral arms. They exist in gravitational fields that are still recovering from the collision, fields that won't fully settle into stable configurations until the merger completes billions of years later. With each subsequent passage, the disruption becomes more severe. More stars are scattered into chaotic orbits. More of the organized disk structure is destroyed. The differential rotation that originally created and maintained spiral structure now works against reforming those structures, winding up any temporary spiral patterns that emerge and dispersing them across the disk. By the third or fourth passage, recognizable spiral structure has essentially disappeared from both galaxies. What remains are amorphous disks containing stars on increasingly randomized orbits. Some stars still move roughly in the plane of the original disks, but their orbital eccentricities have increased, creating puffed-up structures that are thicker than the original thin disks. Other stars have been scattered completely out of the disk, flung into the growing halo by gravitational encounters with density waves or with the other galaxy's mass distribution. These scattered stars contribute to the transition from a disk-dominated galaxy to a more spheroidal structure, one of the key steps in transforming spiral galaxies into elliptical galaxies. The final merger, when the two systems settle into a bound configuration and begin violent relaxation toward equilibrium, completes the transformation. The remaining disk stars mix with the scattered halo population, creating a smooth distribution where stars orbit in all directions rather than following the organized patterns of a rotating disk. The galaxy has transitioned from a spiral to an elliptical, from an organized structure with clear rotational support to a pressure-supported system where stars orbit on essentially random trajectories. This transformation from spiral to elliptical represents one of the most fundamental changes a galaxy can experience, comparable to a caterpillar transforming into a butterfly, except in this case the butterfly is less interesting than the caterpillar. Spiral galaxies are beautiful, dynamic objects with clear structure, ongoing star formation, and rich interstellar media. Elliptical galaxies are comparatively dull, featureless ellipsoids containing old stars with little ongoing activity. But the transformation has deeper consequences than just changes in appearance. The destruction of spiral structure also destroys the mechanisms that funnel gas towards star-forming regions. In spiral galaxies, density waves compress gas as it flows through spiral arms, creating the high-density regions needed for star formation. The regular organized motion of gas through these density waves maintains steady star formation rates for billions of years. When spiral structure is destroyed, this mechanism stops working. Gas no longer flows through regularly spaced density waves that compress it efficiently. Instead, gas motions become more chaotic, with turbulence and random encounters determining where compression occurs. Star formation continues for a while, driven by the remaining gas supply and ongoing turbulence from the merger, but it becomes less efficient, less able to convert gas into stars. Moreover, feedback from the starburst itself works to suppress future star formation. The supernovae and stellar winds from massive stars inject enormous amounts of energy into the interstellar medium, heating gas to temperatures too high for gravitational collapse. This hot gas expands, filling the superbubbles and supershells created by stellar feedback. Eventually, some of this heated gas reaches velocities exceeding the galaxy's escape velocity, and leaves the system entirely expelled into intergalactic space by the violence of the starburst. Simulations suggest that perhaps 30 to 50% of the pre-merger gas supply is expelled from the merged galaxy through this feedback-driven outflow mechanism. The gas doesn't disappear from the universe. It remains in the intergalactic medium surrounding Milkomeda, but it's no longer available for star formation within the galaxy itself. This loss of gas supply, combined with the conversion of much of the remaining gas into stars during the starburst, leaves the merged galaxy relatively gas-poor compared to its spiral progenitors. By the time Milkomeda settles into equilibrium, perhaps only 10 to 20% of the original gas supply remains in the galaxy, and much of that remaining gas is too hot or too dispersed to form stars efficiently. The galaxy has transitioned from a gas-rich star-forming spiral to a gas-poor quiescent elliptical, a transformation driven by the combination of starburst consumption and feedback-driven expulsion. This transition marks the effective death of the galaxy as a living, evolving system. Spiral galaxies are alive in a sense, continuously forming new stars, evolving chemically as massive stars synthesize heavy elements and return them to the interstellar medium, developing new structure through density waves and spiral arms. Elliptical galaxies are dead, containing mostly old stars with little ongoing activity, slowly fading as their stellar populations age, and no new stars form to replace those that die. The transformation from living spiral to dead elliptical is irreversible on timescales relevant to galaxy evolution. Once the gas supply is exhausted or expelled, and once the spiral structure is destroyed, the galaxy cannot easily return to its previous state. New gas could potentially fall back into the galaxy from the surrounding intergalactic medium over billions of years, but without the organized rotation and spiral structure that characterize the original disk, this gas wouldn't efficiently form new stars. Milkomeda will spend the rest of its existence, potentially trillions of years, as a red and dead elliptical galaxy, slowly fading as its stellar population ages. The violent merger that created it will be long forgotten, visible only in subtle features like the distribution of stellar orbits or the chemical composition of its stars, archaeological evidence of a catastrophe that ended two galaxies' lives and created a cosmic graveyard. And this transformation, this death of galaxies through merger, is happening throughout the universe. Every major galaxy merger follows similar patterns, destroying spiral structure, triggering starbursts, expelling gas, and producing elliptical galaxies. The universe is filled with the corpses of spiral galaxies, transformed into featureless ellipsoids by collisions that occurred billions of years ago. Some of these merger remnants are visible in telescopes, captured in various stages of their transformations. These observational examples allow us to see what the Milky Way Andromeda collision might look like from the outside, providing a cosmic preview of our own galaxy's death. Part 4. Cosmic Mirrors. You don't have to imagine what the Milky Way Andromeda collision will look like. The universe has provided examples, galaxy mergers at various stages of their violent dances, captured in exquisite detail by telescopes like Hubble. These cosmic laboratories show us our future written across billions of light years, snapshots of galactic death frozen in time and light. The most spectacular example sits roughly 45 million light-years away in the constellation Corvus. NGC 4038 and NGC 4039, better known as the Antennae galaxies, are currently locked in a merger that began hundreds of millions of years ago and won't complete for hundreds of millions of years more. When you look at images of the antennae, you're seeing what the Milky Way and Andromeda might look like approximately 1 billion years after their first collision. The name comes from the two long tidal tails that extend from the merging cores, graceful arcs of stars stretching more than 300,000 light-years into intergalactic space. These tails form exactly as theory predicts. As the two galaxies passed through each other during their first encounter, tidal forces pulled stars and gas away from the main bodies, creating streamers that follow the orbital trajectories of the galaxies. The material in these tails will eventually fall back into the merged system or escape entirely, becoming intergalactic wanderers. But the tails are only the most visible feature. The cores of the Antennae galaxies tell a more violent story. Where the two galactic centers are approaching each other, Hubble images reveal intense blue. Regions, superstar clusters containing millions of young, hot stars packed into volumes only a few tens of light-years across. These clusters form during collision-triggered starbursts, created when gas clouds from both galaxies crash together and compress to densities high enough for massive star formation. Some of these superstar clusters contain as much mass as globular clusters, the ancient spherical collections of stars that orbit in galactic halos. But unlike globular clusters, which formed billions of years ago and contain only old stars, These merger-induced clusters are brand new, containing stars only a few million years old. They represent star formation occurring at intensities rarely seen in the universe. Brief but spectacular bursts of stellar birth triggered by cosmic violence. Between the bright star clusters, Hubble detects vast clouds of glowing gas, HI regions ionized by ultraviolet radiation from the young massive stars. Some of these emission nebulae span thousands of light years, glowing with the characteristic red light of hydrogen recombination. The scene looks like cosmic fireworks, brilliant points of blue starlight embedded in glowing red clouds, all set against the chaotic backdrop of colliding galactic disks. The antennae galaxies also show what happens to spiral structure during mergers. Neither galaxy retains recognizable spiral arms. The original disk structures have been completely disrupted, pulled apart by tidal forces and scattered through the collision zone. What remains are amorphous distributions of stars and gas, chaotic arrangements that bear no resemblance to the graceful spirals that existed before the collision. X-ray observations of the antennae reveal additional violence invisible to optical telescopes. The Chandra X-ray Observatory detected dozens of bright X-ray sources scattered throughout the merging system. Many of these sources are young supernova remnants, the expanding shock waves from massive stars that formed in the starburst and have already exploded. Others are neutron stars and black holes, the remnants of even earlier stellar deaths, now visible because they're accreting material from companion stars and heating it to X-ray temperatures. The presence of so many supernova remnants confirms that starburst star formation produces predominantly massive stars. These stellar giants live only a few million years before exploding, so finding dozens of recent supernova indicates that the starburst began only recently in cosmic terms, perhaps 10 to 20 million years ago when the galaxies made one of their close passages. Radio observations add yet another layer to the story. The Very Large Array detected intense radio emission from the collision zone, radiation produced by energetic electrons spiraling through magnetic fields. These electrons are accelerated to near-light speed by supernova shocks, creating synchrotron radiation that glows brightly at radio wavelengths. The distribution of radio emission traces the locations of recent supernova activity, showing that stellar violence is concentrated in the regions where gas compression is maximal. But perhaps the most important lesson from the antenna galaxies is the timescale. The merger has been ongoing for hundreds of millions of years, and still has hundreds of millions of years to go before the two cores finally coalesce. This isn't a quick collision. It's a slow-motion catastrophe, unfolding over timescales longer than the entire history of complex life on Earth. For any hypothetical civilization in the antennae galaxies, the merger would define their entire existence. Intelligent life that arose during the merger would have no memory of what the galaxies looked like before collision. The spectacular tidal tails, the intense starburst regions, the chaotic distribution of stars and gas, all of this would be normal for them. Only by studying the orbital motions of stars and reconstructing the dynamical history could they determine that their home system resulted from a collision between two previously separate galaxies. Another spectacular merger example is NGC 2207 and IC 2163, two spiral galaxies caught in the early stages of collision. Unlike the antennae, which are well into their merger sequence, NGC 2207 and IC 2163 are experiencing what might be their first close passage, similar to what the Milky Way and Andromeda will experience during their initial encounter 4 billion years from now. The galaxies still retain recognizable spiral structures, though both are significantly distorted. IC 2163, the smaller of the two, shows dramatic tidal distortion. One of its spiral arms has been pulled into a long streamer extending toward NGC 2207, material being tidally stripped during the close encounter. The arm stretches for tens of thousands of light years, a bridge of stars and gas connecting the two systems. NGC 22107, the larger galaxy, appears less disturbed, but careful analysis reveals subtle asymmetries in its spiral structure. The arms on the side nearest IC 2163 are compressed and brightened, showing where tidal forces from the smaller galaxy have enhanced the existing spiral density waves. The arms on the far side appear more normal, less affected by the ongoing interaction. Infrared observations of NGC 2207 and IC 2163 reveal intense star formation, occurring in the regions where tidal compression is strongest. The Spitzer Space Telescope detected bright infrared emission from warm dust heated by young stars, signatures of starburst activity triggered by the collision. The star formation rate in both galaxies has increased substantially compared to isolated spirals of similar mass, demonstrating how galaxy interactions enhance stellar birth. But NGC 2207 and IC 2163 also demonstrate that first passages don't immediately destroy spiral structure. Both galaxies still look recognizably like spirals, even though they're clearly interacting. It's only after multiple passages, after repeated tidal disruptions, that spiral structure completely dissolves into the chaotic distribution seen in systems like the antennae. This progressive destruction of spiral structure provides a timeline for the Milky Way Andromeda collision. After the first passage, 4 billion years from now, both galaxies will still show spiral arms, though distorted and stretched by tidal forces. Only after the second and third passages, 4.5 to 5 billion years from now, will the spiral structures completely dissolve, transforming the system into something more like the antennae galaxies. The mice galaxies, NGC 4676, provide yet another perspective on galaxy mergers. These two spirals are named for their long tidal tails, which extend behind them like the tails of mice. The merger is more advanced than NGC 2207 and IC 21163, but less advanced than the antennae, showing an intermediate stage where spiral structure is badly disrupted but the galactic cores haven't yet merged. What makes the mice particularly instructive is the detailed structure visible in their tidal tails. Hubble images reveal that the tails aren't smooth distributions of material. Instead, they contain numerous bright knots, regions where matter is concentrated during the tidal stripping process. Some of these knots are dense enough that they might survive as independent stellar systems, small satellite galaxies born from the debris of the merger. This demonstrates that galaxy mergers don't just destroy structure, they can also create new structures from tidal debris. Some of the dwarf galaxies orbiting large galaxies might be tidal dwarfs, formed from material stripped during ancient mergers, rather than primordial galaxies that have survived since the universe's youth. The tidal tails in the mice also show star formation occurring in the stripped material. Young blue stars dot the tails, indicating that gas in the stripped streamers has compressed enough to trigger gravitational collapse, despite being pulled away from the parent galaxies. These stars form in one of the most extreme environments imaginable, tidal debris flying through intergalactic space at hundreds of kilometers per second, yet somehow managing to create the density concentrations needed for stellar birth. All of these merger examples share common features: tidal tails stretching hundreds of thousands of light years, starburst regions where collision-triggered star formation creates brilliant blue star clusters, disrupted spiral structures transforming into chaotic distributions, HII regions glowing with the red light of ionized hydrogen, supernova remnants marking the deaths of massive stars. These features appear in every major merger, regardless of the galaxy's specific properties or the geometry of their collision. The universality of these features confirms that computer simulations of galaxy mergers capture the essential physics. When simulations predict tidal tail formation, we see tidal tails in real mergers. When simulations predict collision-triggered starbursts, we detect intense star formation in merger systems. When simulations predict the destruction of spiral structure, we observe exactly that progression in galaxies at various merger stages. This gives us confidence that simulations of the Milky Way Andromeda collision accurately predict our future. The detailed predictions about tidal forces, starburst intensities, timescales, and final outcomes aren't speculation. They're based on physical models that have been tested against dozens of observed merger systems and found to reproduce the key features accurately. But observing distant mergers also reveals details that simulations struggle to capture: the internal structure of superstar clusters, the chemical composition of gas in tidal tails, the distribution of stellar ages in merger remnants. These fine details require observations of real systems, and they provide crucial constraints that help refine simulations and improve our understanding of merger physics. 90-minute hook point, word count. 72,500. When the merger completes and Milkomeda settles into its final form, what exactly will emerge from the debris? The answer is written in the properties of elliptical galaxies, those featureless ellipsoids that represent the end state of major galaxy mergers throughout the universe. Elliptical galaxies range from small systems containing only a few billion stars to giant ellipticals containing trillions of stars, vastly more massive than any spiral galaxy. Milkomeda will be a large elliptical, containing roughly 1 trillion stars from the combined Milky Way and Andromeda populations, plus new stars formed during the merger starbursts. In terms of total stellar mass, it will rank among the more massive galaxies in the local supercluster. The galaxy's shape will be roughly ellipsoidal, elongated in 1 or 2 dimensions rather than perfectly spherical. The exact ellipticity will depend on the orbital parameters of the collision and the angular momentum of the merged system. Simulations predict axis ratios ranging from nearly spherical to moderately flattened, but definitely not disk-like. The thin disk structure that characterizes spiral galaxies will be completely absent. Stars in Milkomeda will orbit on 3-dimensional trajectories rather than the organized circular orbits found in spiral disks. Think of it like the difference between traffic on a highway, where all cars move in the same direction on defined lanes, versus traffic in a crowded parking lot, where cars move in all directions. Spiral galaxy disks are like highways. Elliptical galaxies are like parking lots. This fundamental difference in orbital structure affects everything about the galaxy. Without organized disk rotation, there are no density waves to maintain spiral arms. Without spiral arms, there are no regular compression zones to trigger star formation. The galaxy becomes dynamically hot, a technical term meaning that stars have large random velocities rather than moving in organized patterns. The velocity dispersion, the spread of velocities among stars at any given location, will be several hundred kilometers per second in Milkomeda. This compares to roughly 30 to 50 kilometers per second in the current Milky Way disk. Stars will zip past each other at high relative velocities, creating a dynamic environment where the local stellar neighborhood changes completely on timescales of millions of years. From the perspective of any surviving planetary system, the night sky would change noticeably over the lifetime of a civilization. Stars that are currently neighbors would drift apart. New stars would approach from unexpected directions. Over millions of years, the familiar constellations would dissolve and reform in completely different patterns. The sky would be in constant flux, a slowly churning pattern of stellar motion visible to civilizations patient enough to observe over long timescales. But the most obvious difference would be the lack of the Milky Way's characteristic band of light stretching across the sky. In the current Milky Way, we see this band because we're looking along the thin disk from inside it, seeing the combined light of billions of distant stars all concentrated in the galactic plane. From within Milkomeda, the stellar distribution would be more isotropic, stars scattered in all directions rather than concentrated in a single plane. The sky might be brighter on average. Milkomeda contains more stars than the current Milky Way, but the light would be distributed more uniformly across the celestial sphere. no bright band crossing the sky, no dark dust lanes blocking regions of the disk, just a more or less uniform glow from stars in all directions, brighter near the galactic centre and fainter toward the outskirts. The galactic centre itself would be invisible to optical observation from most locations. The centre of Milkomeda will contain a dense concentration of old stars, including the merged supermassive black hole, all embedded in a thick soup of stellar remnants, white dwarfs, neutron stars and black holes. This central region will be so crowded with matter and so laden with dust from stellar winds that visible light cannot penetrate. Only infrared and radio observations could peer into the core, but the outer regions of Milkomeda will be relatively transparent. With star formation essentially ceased, there will be little new dust production to obscure the view. Distant galaxies will be visible from within Milkomeda with less obscuration than we currently experience looking through the Milky Way's dust-laden disk. This might seem like a benefit for hypothetical astronomers in Milkomeda, clearer views of the distant universe. However, those clear views will reveal an increasingly empty cosmos. The universe's expansion will have continued during the billions of years the merger takes to complete. Distant galaxies will have moved farther away, their recession velocities increased by cosmic expansion. Many galaxies visible in today's sky will have receded beyond the cosmic horizon, unreachable by any signal travelling at light speed or slower. Milkomeda will find itself increasingly isolated in an expanding universe. The local group of galaxies, the collection of 80+ galaxies gravitationally bound with the Milky Way and Andromeda, will have completely merged into Milkomeda or its immediate satellites. Most of these smaller galaxies will be consumed during the merger, their stars absorbed into the growing elliptical. Only a few of the most distant dwarfs might survive as satellites orbiting the merged galaxy. Beyond the local group, the universe will be emptying. The Virgo cluster, currently our nearest large galaxy cluster about 50 million light-years away, will still be visible, but its member galaxies will have merged with each other, transforming the cluster into a collection of large elliptical galaxies rather than the mix of spirals and ellipticals we see today. Other nearby clusters will undergo similar evolution. The globular clusters that currently orbit both the Milky Way and Andromeda will survive the merger largely intact. These ancient spherical star clusters, containing hundreds of thousands to millions of old stars each, are dense enough and massive enough that tidal forces during the merger won't disrupt them. They'll simply be added to Milkomeda's globular cluster system, giving the merged galaxy perhaps 500 to 600 globular clusters compared to the Milky Way's current 150 or so. These globular clusters will be among the oldest objects in Milkomeda, stellar populations that formed 12 to 13 billion years ago when the universe was still young. Many contain stars nearly as old as the universe itself, ancient suns that witnessed cosmic dawn. In Milkomeda, these clusters will serve as archaeological sites, fossils from a time before either the Milky Way or Andromeda existed as separate galaxies. The planetary nebulae, those beautiful shells of gas ejected by dying sun-like stars, will also persist in Milkomeda. Every sun-like star that dies during or after the merger will create a planetary nebula, adding to the population of these glowing ghosts. For a few tens of thousands of years, each nebula glows brightly as ultraviolet radiation from the central white dwarf ionizes the expanding shell. Then the nebula fades, its material dispersing into the interstellar medium. At any given time, Milkomeda will contain hundreds of thousands of active planetary nebulae, glowing shells scattered throughout the galaxy. From a distance, these nebulae would be too faint to see individually, but their combined light would contribute a faint glow to the galaxy's spectrum. Deep images of Milkomeda would reveal countless faint nebulae, tiny rings and shells marking stellar deaths throughout the system. The supernova rate will decline dramatically after the merger completes. During the starburst phases, supernovae occur at rates tens to hundreds of times higher than in normal spiral galaxies. But after the gas is exhausted and star formation ceases, the supernova rate drops to nearly zero. The only supernova will be type Ia events, white dwarf explosions in binary systems, occurring perhaps once every few centuries rather than the dozens to hundreds per century during the starburst. This creates a galaxy that's remarkably quiescent compared to the violent merger phase. No massive starbursts, few supernovae, little dust obscuration, minimal gas dynamics. Milkomeda will be a peaceful place compared to the chaos of the merger, a cosmic retirement home for aging stellar populations. But peaceful doesn't mean unchanging. Stellar evolution continues, gradually transforming the stellar population over trillions of years, and one specific stellar system deserves special attention: the fate of our Sun and Earth during this cosmic transformation. The Sun currently orbits roughly 26,000 light-years from the Milky Way's centre, placing us in the outer disk where stellar densities are relatively low and conditions are stable. During the merger, the Sun's orbit will be completely disrupted. The gravitational fields of both galaxies will perturb the Sun's trajectory, potentially sending it on a completely different path through the merged system. Simulations suggest roughly a 12% chance that the Sun will be ejected from the galactic disk entirely during the merger, flung into the halo or even into intergalactic space by gravitational interactions with density waves or tidal features. If this happens, the solar system would drift away from the galactic centre, gradually increasing its distance from the main body of stars until it becomes an isolated system in the dark spaces between galaxies. From one perspective, this would be catastrophic. Cut off from the galactic community, any advanced civilization in the solar system would lose access to the rich stellar environment of the galactic disk. From another perspective, ejection might be the safest outcome. The halo is quiet and empty, far from the radiation hazards of starbursts and the gravitational chaos of the merger zone. The more likely outcome, 88% probability according to most simulations, is that the Sun remains within Milkomeda but on a different orbit than its current trajectory. The Sun might end up closer to the galactic centre, in the dense inner regions where stellar encounters are more frequent, or it might be scattered to larger radii, in the sparse outer reaches where neighbouring stars are rare. Each scenario carries different implications for any surviving planetary system. An orbit in the inner galaxy increases the probability of close stellar encounters, events where other stars pass within a few light-years of the Sun. These encounters could gravitationally perturb the outer solar system, potentially scattering comets from the Oort cloud toward the inner planets, or even disrupting the orbits of Neptune or Uranus over very long timescales. An orbit in the outer galaxy reduces encounter rates, but also means longer orbital periods around the galactic centre. The Sun currently takes roughly 225 million years to complete one galactic orbit. In the outer regions of Milkomeda, orbital periods could extend to 500 million years or more. The Sun would spend more time in the sparse outer regions, seeing fewer stars in the sky but experiencing a more stable gravitational environment. But these considerations assume the Earth and Solar System still exist in recognisable form 4 billion years from now. That's far from certain. The Sun's evolution as a star proceeds independently of the galactic merger, following a timeline determined by nuclear fusion physics in the stellar core. In approximately 5 billion years, roughly a billion years after the Milky Way Andromeda collision begins, the Sun will exhaust the hydrogen fuel in its core. When this happens, the core will contract and heat up, while the outer envelope expands dramatically. The Sun will transform from a yellow dwarf star into a red giant, growing to perhaps 100 times its current radius. At maximum expansion, the Sun might engulf the orbits of Mercury and Venus, possibly even Earth. Recent models suggest Earth might survive if the Sun loses enough mass during its red giant phase to push planetary orbits outward through conservation of angular momentum. But even if Earth avoids being literally swallowed, it will be sterilised by the intense heat from the nearby red giant Sun. Surface temperatures will rise to thousands of degrees. The oceans will boil away into space. The atmosphere will be stripped by intense stellar winds. Any life on Earth will be extinguished long before the galactic merger completes. By the time Milkomeda settles into equilibrium 7 billion years from now, Earth will be a scorched rock orbiting a white dwarf remnant, if it survives at all. This timeline means that Earth's fate is sealed by stellar evolution rather than galactic dynamics. The merger might disrupt the solar system's orbit through the galaxy, but it won't directly affect the Sun's evolution or Earth's habitability. The Sun will die on schedule regardless of what happens in the surrounding galaxy. For humanity or any descendants that might exist 5 billion years from now, this creates an interesting decision point. Stay on Earth and accept extinction when the Sun becomes a red giant, or develop the technology to migrate to other star systems before the Sun's evolution makes Earth uninhabitable. The galactic merger provides context for this decision, but doesn't fundamentally change the timeline. Any civilization that survives the Sun's red giant phase will witness the galactic merger from whatever new home they've established. They'll see the slow transformation of the night sky as the merger progresses. They'll watch tidal tails form and dissolve. They'll observe the spectacular starbursts in collision zones. They'll witness the gradual dissolution of spiral structure and the emergence of Milkomeda's elliptical form, and through it all, they'll know that this transformation was inevitable from the moment the Milky Way and Andromeda formed. The merger was written into the laws of physics billions of years before life arose on Earth. No technology, no matter how advanced, could prevent it. The only choice was whether to survive it or perish with the old order. This is the ultimate lesson of galactic death. It's inevitable, predictable, unstoppable, and utterly indifferent to anything that might live within the dying galaxies. The universe operates according to gravity and momentum, forces that care nothing for life or civilization, or the billions of years of evolution that created complex organisms capable of understanding their own cosmic fate. The galaxies will die, Milkomeda will be born, and eventually, even Milkomeda will fade into darkness as its stellar populations age, and the universe continues its inexorable expansion toward heat death. This is the cosmic catastrophe protocol, playing out over timescales that dwarf human history, but following rules we can understand and predict with startling precision. Part 5. The Long Twilight. The merger completes. Milkomeda settles. The violence ends. And then begins the longest chapter in galactic history, a slow fade into darkness that will make everything that came before seem like a brief flash of light in an eternity of night. 7 billion years from now, when Milkomeda has fully relaxed into its equilibrium elliptical configuration, the galaxy will contain roughly 1 trillion stars. Most are young, formed during the starburst phases of the merger. Blue massive stars still dot the galaxy, though they're dying rapidly now that the gas supply has been exhausted. White and yellow stars like the Sun, middle-aged residents inherited from the pre-merger Milky Way and Andromeda, make up a substantial fraction of the stellar census. And throughout the galaxy, scattered like embers in darkness, the red dwarfs wait. Red dwarfs are the universe's minimalists, stars containing only 8 to 50% of the Sun's mass, burning hydrogen so slowly that the least massive among them will shine for trillions of years. The Sun will die in 10 billion years total, exhausting its hydrogen and swelling into a red giant before collapsing to a white dwarf. But a red dwarf containing only 10% of the Sun's mass will burn hydrogen for more than 10 trillion years, 1,000 times longer than the current age of the universe. These dim red stars represent the future of stellar illumination in Milkomeda and throughout the universe. As the more massive stars die over the next few tens of billions of years, red dwarfs will increasingly dominate the galaxy's stellar population. Not in total luminosity, they're far too dim for that, but in sheer numbers. By the time Milkomeda reaches an age of 100 billion years, roughly 7 times the current age of the universe, red dwarfs will constitute the vast majority of stars still burning hydrogen. The transition happens gradually, a slow winnowing of stellar populations as physics removes the brightest stars first. The blue, massive stars, those brilliant beacons that dominated the starburst phase, die first. Most have already exploded as supernovae by the time the merger completes. The few stragglers burn out within the first few million years after the merger ends. Their lives are spectacular but brief, compressed into timescales shorter than the age of complex life on Earth. Next to fade are the white and blue-white stars, those containing 5 to 20 times the Sun's mass. These stars live for tens to hundreds of millions of years, bright enough to dominate their local regions but not bright enough to outshine entire star clusters like the most massive stars do. They die as supernovae if massive enough, or as planetary nebulae if they fall just below the supernova threshold. Either way, they disappear from the stellar census within a few hundred million years after the merger completes. By 10 billion years after merger completion, roughly 17 billion years after the Big Bang, stars like the Sun begin dying in large numbers. The Sun-like stars inherited from the pre-merger galaxies reach the ends of their 10 billion year lifetimes, swelling into red giants, shedding their outer layers as planetary nebulae and collapsing to white dwarfs. The stars formed during the merger starbursts, younger but otherwise similar to the Sun, still have billions of years remaining, but they too will eventually follow the same path. The death of Sun-like stars marks a critical transition in galactic evolution. These stars, containing roughly 0.8 to 1.2 solar masses, represent a peak in the stellar initial mass function. More stars form in this mass range than in any higher mass range. So when Sun-like stars begin dying in large numbers, the galaxy's luminosity decreases noticeably. The overall light output doesn't plummet. Lower mass stars continue burning, but the spectrum shifts redder as the bright yellow-white light from Sun-like stars gets replaced by the dim red light from smaller stars. By 100 billion years after the Big Bang, Milkomeda has aged roughly 7 times longer than the current age of the universe. The galaxy has become a predominantly red elliptical, exactly what astronomers observe when they look at old elliptical galaxies in the distant universe. Most of the stellar population consists of red dwarfs still burning hydrogen, plus the growing population of stellar remnants, white dwarfs, neutron stars, and black holes left behind by generations of stellar deaths. The galaxy's luminosity has decreased to perhaps 10% of its peak value during the starburst phase. Most of the light comes from red dwarfs, those dim embers that will continue glowing for trillions of years. If you could observe Milkomeda from a distant galaxy at this point, it would appear as a reddish elliptical galaxy, unremarkable among the billions of similar galaxies that populate the universe at this late epoch. But the story of stellar evolution continues for trillions of years beyond this point. The red dwarfs, those patient stars, continue burning hydrogen through mechanisms their more massive cousins exhausted billions of years ago. The least massive red dwarfs, those containing only 8 to 10% of the Sun's mass, are fully convective. Currents of plasma cycle material from the core to the surface and back, mixing fresh hydrogen from the outer layers into the core where it can be burned. This allows them to use essentially all their hydrogen, rather than just the fuel in the core, extending their lifetimes to truly astronomical durations. A red dwarf containing 8% of the Sun's mass will shine for approximately 12 trillion years. That's roughly 900 times the current age of the universe. These stars began forming when galaxies first assembled, roughly 13 billion years ago. They're currently only about 1,000th of the way through their lifetimes. They have barely begun their patient vigil, waiting trillions of years before they finally exhaust their fuel and fade to darkness. The universe will change beyond recognition during the red dwarf era. Star formation has essentially ceased throughout the cosmos by 100 billion years after the Big Bang. The gas supplies in galaxies have been consumed or expelled. No new stars are forming to replace those that die. The stellar populations that exist at that point represent the last generation, the final cohort of stars that will ever shine through nuclear fusion. As the universe ages from 100 billion to 1 trillion years, the stellar populations continue evolving. More sun-like stars die, swelling into red giants and collapsing to white dwarfs. The stars slightly more massive than the Sun, those containing 1.2 to about 3 solar masses, finally reach the ends of their lifetimes, having burned for hundreds of billions to trillions of years. They too become white dwarfs, adding to the growing population of stellar corpses. By 1 trillion years after the Big Bang, roughly 70 times the current age of the universe, essentially, all stars more massive than red dwarfs have died. The galaxy contains no bright stars, no sun-like yellow stars, no orange stars. Only red dwarfs still burn hydrogen, along with a vast population of white dwarfs, neutron stars and black holes left behind by previous stellar generations. The galaxy's luminosity has decreased to less than 1% of its peak value. Most of the light comes from the dimmest red dwarfs, stars so faint that a single sun-like star outshines millions of them. If you could observe Milkomeda from a distance at this point, it would be barely detectable, a faint red glow marking the location of a galaxy that once blazed with the light of billions of bright stars. From within the galaxy, the night sky would be profoundly dark. The stellar density in elliptical galaxies like Milkomeda is lower in the outer regions than in spiral galaxy disks. A planet orbiting a red dwarf in the outer parts of Milkomeda would see relatively few stars in the sky. Perhaps a few hundred to a few thousand stars visible to the naked eye, compared to the several thousand visible from Earth today. And those visible stars would all be dim red embers, none brighter than the faintest stars visible in our current night sky. The universe itself would be almost invisible. By 1 trillion years after the Big Bang, cosmic expansion will have carried nearly all other galaxies beyond the cosmic horizon. The light from distant galaxies will have been stretched by expansion to wavelengths so long that it becomes undetectable. The cosmic microwave background radiation, currently at a temperature of 2.7 Kelvin, will have cooled to a tiny fraction of 1 Kelvin, essentially indistinguishable from perfect vacuum. Any hypothetical civilization existing in Milkomeda at this point would observe a universe that appears to contain only their own galaxy, surrounded by darkness. They would have no evidence of cosmic expansion, no cosmic microwave background to measure, no distant galaxies to study. Their cosmological models would necessarily be completely different from ours, based on the limited evidence available from their isolated galactic island. But even the red dwarfs won't last forever. The era from 1 trillion to 10 trillion years after the Big Bang sees the gradual extinction of even these patient stars. The most massive red dwarfs, those containing 40 to 50% of the Sun's mass, burn through their hydrogen over timescales of a few trillion years. They swell slightly as they exhaust their fuel, then collapse to white dwarfs much like the Sun will, just on vastly longer timescales. As each red dwarf dies, the galaxy loses one more light source. The stellar census continues its inexorable decline. By 10 trillion years after the Big Bang, perhaps half the original red dwarf population has died, joining the white dwarf population that already constitutes the majority of stellar remnants in the galaxy. The remaining red dwarfs, those containing less than 30% of the Sun's mass, continue their slow burn. But their numbers decrease steadily over the next trillion years as the smaller members of this population exhaust their fuel and fade. By 20 trillion years after the Big Bang, perhaps only the least massive red dwarfs remain, those containing 8 to 15% of the Sun's mass, stars so dim that a single sun-like star outshines hundreds of millions of them, and still they burn, patiently, steadily, converting hydrogen to helium at rates measured in quintillionths of a solar mass per year, so slowly that individual atoms at the surface might wait millions of years before cycling into the core to be fused. But the process continues, maintaining a faint glow against the growing darkness. The universe at 20 trillion years after the Big Bang is a profoundly different place from the universe we inhabit. Star formation ceased 19.9 trillion years ago. Nearly all stars that will ever exist have already died. The cosmic expansion has accelerated to the point where our galaxy and a handful of gravitationally bound companions are the only structures visible in an otherwise empty universe. The cosmic microwave background has cooled to temperatures measured in billionths of a Kelvin, essentially indistinguishable from absolute zero. But a few lights still shine. Those patient red dwarfs, the smallest stars capable of sustaining hydrogen fusion, continue their vigil. They will burn for thousands of trillions of years more, the last stars in a dying universe, maintaining a feeble protest against the encroaching darkness. Eventually, even they must fade. The timeline varies depending on the star's exact mass and composition, but the least massive red dwarfs capable of fusion, those barely massive enough to ignite hydrogen burning in their cores, will exhaust their fuel roughly 10 to 12 trillion years after they form. The youngest of these stars, those born during the final gasps of star formation roughly 100 billion years after the Big Bang, will burn until approximately 12 trillion years after the Big Bang. When the last red dwarf exhausts its hydrogen and collapses to a white dwarf, perhaps 12 to 13 trillion years after the Big Bang, the era of stellar nucleosynthesis ends forever. No more stars burn hydrogen. No more stars generate energy through nuclear fusion. The only light in the universe comes from the fading glow of white dwarfs, cooling stellar remnants that radiate away the heat accumulated during their progenitor stars' lives. This marks the end of the stelliferous era, the age when stars dominated the universe's energy output. The universe transitions to the degenerate era, named for the degenerate matter that makes up white dwarfs. This era will last far longer than the stelliferous era, stretching from roughly 13 trillion years after the Big Bang to perhaps 10 to the power of 40 years after the Big Bang, when even white dwarfs fade to complete darkness. 1 to 5 the minute hook, word count, and 86,500. The degenerate era unfolds slowly. White dwarfs cool according to well-understood thermal physics, radiating away their internal heat over timescales of trillions to quadrillions of years. A white dwarf begins its cooling sequence at temperatures of 100,000 Kelvin or more, hot enough to glow white hot, hence the name. But with no internal energy source, no fusion to generate new heat, the white dwarf can only cool. The cooling proceeds exponentially. The hotter the white dwarf, the faster it radiates energy. Young white dwarfs, those freshly formed from red, giants or planetary nebulae, cool quickly at first, dropping from 100,000 Kelvin to 10,000 Kelvin in only a few billion years. But as they cool, the rate of energy loss decreases. Cooling from 10,000 Kelvin to 5,000 Kelvin takes tens of billions of years. From 5,000 to 3,000 takes hundreds of billions of years. The oldest white dwarfs in Milkomeda, those formed when sun-like stars died roughly 10 billion years after the Big Bang, have had trillions of years to cool by the time the last red dwarf dies. These ancient remnants glow with temperatures of only a few thousand Kelvin, too cool to emit visible light. They shine only in the infrared, visible to the human eye, barely distinguishable from the cold darkness of space, but they still shine. The heat accumulated during billions of years of stellar fusion radiates away into space, slowly but steadily. The white dwarf continues cooling through 3,000 Kelvin, then 2,000, then 1,000. Each step takes longer than the last. Cooling from 1,000 Kelvin to 100 Kelvin requires quadrillions of years, time periods longer than the entire stelliferous era by factors of millions. The younger white dwarfs, those formed more recently from the dying red dwarfs, begin their cooling sequences at various temperatures depending on the mass and composition of their progenitor stars. But all follow the same inexorable path, radiating away their heat over timescales that stretch toward eternity, gradually approaching the temperature of the cosmic microwave background. The cosmic microwave background itself continues cooling throughout this era. The universe's expansion stretches the wavelength of this primordial radiation, reducing its temperature inversely proportional to the scale factor. At 1 trillion years after the Big Bang, the cosmic microwave background has cooled to roughly 0.03 Kelvin. By 10 trillion years, it reaches 0.03 Kelvin. By 100 trillion years, 0.03 Kelvin. The cooling proceeds inexorably. The universe expands, the background radiation cools, and eventually, on timescales measured in 10 to the power of 20 years or more, the coolest white dwarfs reach the temperature of the cosmic microwave background. At that point, they achieve thermal equilibrium with the universe. They can cool no further. They've become black dwarfs, completely dark stellar remnants at the same temperature as the void surrounding them. Black dwarfs represent the final state of stellar evolution for low and medium mass stars. Dense, Earth-sized spheres containing roughly half to a full solar mass compressed into a volume comparable to a planet. Made primarily of carbon and oxygen, the ashes of hydrogen and helium fusion, held up against gravitational collapse by electron degeneracy pressure, a quantum mechanical effect that prevents electrons from being compressed beyond a certain density. Black dwarfs emit no light. They produce no energy. They simply exist, cold and dark, crystalline spheres of carbon and oxygen, drifting through an expanding universe that has cooled to near absolute zero. If you could somehow visit a black dwarf, you'd find a solid surface, a diamond-like structure stretching across an Earth-sized world. The gravity at the surface would be hundreds of thousands of times stronger than Earth's gravity, strong enough to compress you to atomic thinness in an instant. Not that you'd want to visit. The black dwarf exists at nearly absolute zero temperature, dark against an equally dark universe. No light to see by, no heat to detect, just a cold, dead world marking where a star once burned. Milkomeda, by the time the last white dwarfs cool to black dwarfs, contains perhaps 500 billion to a trillion of these dark remnants. The exact number depends on the initial stellar populations and the mass distribution of stars, but every star originally containing less than about 8 solar masses ends as a white dwarf, and eventually as a black dwarf. That represents roughly 95% of all stars ever formed. The remaining 5%, the massive stars that exploded as supernovae, left behind either neutron stars or black holes. Milkomeda contains perhaps 10 to 50 billion neutron stars, dense stellar remnants containing 1 to 2 solar masses compressed into spheres only 20 kilometers in diameter. These neutron stars, like white dwarfs, cool over time, radiating away the heat from their formation. But they cool much faster than white dwarfs because of their smaller size and different emission mechanisms. By the time white dwarfs cool to black dwarfs, neutron stars have long since faded to darkness. They become cold, dark spheres of degenerate neutrons, too small to see even if they weren't cold, too dense to comprehend, relics from an age when massive stars exploded and created the heavy elements that make planets possible. And scattered throughout Milkomeda, perhaps numbering in the hundreds of millions to a few billion, stellar mass black holes wait. These are not like the supermassive black hole at the galactic center, the 100 million solar mass monster formed from the merger of Sagittarius A star and Andromeda's central black hole. Stellar mass black holes contain only a few, to perhaps 100 solar masses, remnants of the most massive stars that once lived in both galaxies. Black holes are the only stellar remnants that don't cool through radiation. A black hole has no surface, no material that can emit photons. Once formed, a stellar mass black hole is essentially permanent on timescales shorter than 10 to the power of 67 years. It simply exists, a gravitationally bound region of space-time from which nothing can escape. But black holes can grow. If a black hole encounters other matter, whether gas, stars, or other black holes, it can capture and absorb that matter, adding the captured mass to its own. In the dense central regions of Milkomeda, Where stellar remnants are packed relatively closely, black holes can grow slowly through occasional encounters with other objects. The process is rare. Even in galactic centers, stellar densities are low enough that direct collisions between stellar remnants occur only every few trillion years per black hole. But with hundreds of millions of black holes and timescales stretching toward eternity, these rare events add up. Over quadrillions of years, black holes in the galactic center slowly consume nearby black dwarfs, neutron stars, and other black holes, growing incrementally as they clean up the stellar debris around them. The central supermassive black hole, now containing approximately 100 million solar masses, after growing during the merger and subsequent accretion, also continues growing through captures. Stars and stellar remnants on orbits that pass within a few gravitational radii of the black hole's event horizon can be captured through tidal interactions or close encounters with other stars that perturb them into capture trajectories. Computer simulations of galactic dynamics suggest that over timescales of 10 to 100 trillion years, a substantial fraction of the stars near a galaxy's center, perhaps 10 to 30%, will ultimately be consumed by the central supermassive black hole. This represents perhaps 10 to 30 billion solar masses of material that the black hole can capture from the dense stellar population surrounding it. The growth is slow. Even with hundreds of millions of stars available in the central regions, the capture rate might be only 1 star per million years during the early phases, declining as the central regions are depleted. But over 100 trillion years, that adds up. The central black hole could grow from 100 million solar masses to perhaps 130 to 140 million solar masses, a substantial increase even if it represents only a small fraction of the galaxy's total stellar mass. Meanwhile, the rest of the galaxy is also evolving dynamically. Gravitational interactions between stars and stellar remnants slowly redistribute energy and angular momentum, a process called two-body relaxation. Every time two stars pass relatively close to each other, they exchange energy through gravitational interaction. One star gains energy and moves to a larger orbit. The other loses energy and sinks toward the galactic center. This process operates extremely slowly. The relaxation timescale for a galaxy the size of Milkomeda is roughly 10 to the power of 19 years, far longer than the current age of the universe, but not infinite. Over these immense timescales, the galaxy gradually evaporates. Stars that gain enough energy through gravitational encounters can exceed the galaxy's escape velocity and leave the system entirely, becoming intergalactic wanderers. Simultaneously, stars that lose energy sink toward the galactic center, increasing the central density. This creates a runaway process where higher central density leads to more frequent encounters, which leads to more energy redistribution, which leads to more evaporation and more central concentration. Eventually, this process results in core collapse, where the central density becomes so high that stellar dynamics become dominated by frequent encounters. But before core collapse can occur, another process intervenes. The central supermassive black hole, growing through captures as described earlier, acts as an energy sink that extracts energy from stars passing close to it. This energy extraction process, called Chandrasekhar dynamical friction, when applied to the black hole's interaction with surrounding stars, removes energy from the stellar distribution and transfers it to the black hole's kinetic energy. The net effect is that the black hole prevents complete core collapse by extracting energy from the core before densities can become extreme. Instead of a singular collapsed core, the galaxy develops a density cusp, a region where density increases steeply toward the center but remains finite, surrounding the central black hole. This evolutionary endpoint, a galaxy consisting mostly of black dwarfs and other stellar remnants, in a slowly evaporating distribution, with a central supermassive black hole slowly consuming the innermost stars, represents the stable configuration that Milkomeda will maintain for timescales approaching 10 to the power of 20 years. But even this configuration is not eternal. The universe has secrets. processes operating on timescales so long they dwarf everything discussed so far. Processes that will ultimately dismantle not just galaxies, but the very atoms that make them up. Word count: 93,500. Around 10 to the power of 34 years after the Big Bang, if certain grand unified theories of particle physics are correct, protons begin to decay. Protons are the nuclei of hydrogen atoms and components of all heavier atomic nuclei. They're made of quarks, fundamental particles held together by the strong nuclear force. In all observations ever made, protons appear to be stable. The lifetime of a proton is known to exceed 10 to the power of 34 years from experiments that watch vast numbers of protons for signs of decay. But many grand unified theories, attempts to unify the electromagnetic, weak and strong nuclear forces into a single framework, predict that protons are not truly stable. They decay, but with half-lives so long that detecting individual decays requires watching enormous numbers of protons for extended periods. The predicted lifetime varies depending on the specific theory, but many estimates fall in the range of 10 to the power of 34 to 10 to the power of 36 years. If protons decay with lifetimes in this range, then around 10 to the power of 34 years after the Big Bang, the black dwarfs that make up the majority of Milkomeda's mass will begin to disintegrate. A black dwarf consists primarily of carbon and oxygen nuclei, each containing protons and neutrons. When the protons decay, the nuclei fall apart. The decay is not sudden. With a half-life of 10 to the power of 34 years, half the protons in a black dwarf will decay over that time scale. The other half require another 10 to the power of 34 years to decay. But gradually, over timescales measured in 10 to the power of 35 to 10 to the power of 36 years, the black dwarf evaporates, its constituent protons decaying into lighter particles like positrons, neutrinos, and photons. The neutrons in atomic nuclei are stabilized by their nuclear environment. Isolated neutrons decay in about 15 minutes through weak interactions. But neutrons bound in atomic nuclei can be stable. However, when the protons around them decay, the nuclear binding is disrupted, and the neutrons also decay or are ejected. The end result is that black dwarfs, neutron stars, and all other matter made of atomic nuclei slowly evaporate through proton decay. Where once stood a black dwarf, a crystalline sphere of carbon and oxygen containing half a solar mass, there remains only a diffuse cloud of positrons, electrons, photons, and neutrinos, spreading slowly through space. The same process affects everything made of protons. Planets, if any survived on orbits around black dwarfs, asteroids drifting through space, the remnants of old molecular clouds. Everything made of atoms slowly disintegrates as the protons within them decay into lighter particles. Neutron stars might seem immune to this process since they're made of neutrons rather than protons. But neutron stars also contain some protons in their outer layers and cores. As these protons decay, the neutron star loses mass and eventually evaporates entirely through a combination of proton decay and neutron decay. By 10 to the power of 40 years after the Big Bang, if proton decay occurs with the predicted timescales, essentially all matter made of atoms will have disintegrated. What remains are black holes, the only objects that can survive proton decay because they contain no protons in any conventional sense. Milkomeda at 10 to the power of 40 years after the Big Bang, if we can still call it a galaxy at this point, consists of black holes scattered through an expanding void. The supermassive black hole at the former galactic centre, perhaps containing 150 million solar masses after trillions of years of growth through stellar captures. Hundreds of millions to billions of stellar mass black holes, each containing a few to perhaps 100 solar masses. And nothing else. No stars, no planets, no atoms, just black holes and the diffuse sea of particles and radiation left behind by proton decay. But black holes are not eternal either. In 1974, Stephen Hawking proved that black holes emit thermal radiation through quantum mechanical processes occurring near their event horizons. This Hawking radiation causes black holes to slowly lose mass, evaporating over timescales that depend on their mass. The evaporation timescale scales with the cube of the black hole's mass. A solar mass black hole evaporates in approximately 10 to the power of 67 years. A 10 solar mass black hole takes 10 to the power of 70 years. A 100 million solar mass black hole, like Milkomeda's central supermassive black hole, requires approximately 10 to the power of 98 years to evaporate completely. These timescales dwarf everything discussed so far by factors of trillions of trillions of trillions. The proton decay era, unimaginably long compared to the stelliferous era, is infinitesimal compared to the black hole evaporation era. If the entire history from the Big Bang to proton decay were compressed into 1 second, the black hole evaporation era would last longer than the current age of the universe, raised to the power of several thousand. But given infinite time, even these processes complete. The stellar mass black holes evaporate first, over timescales of 10 to the power of 67 to 10 to the power of 70 years depending on their masses. They begin emitting Hawking radiation at a temperature inversely proportional to their mass. A solar mass black hole has a Hawking temperature of about 60 billionths of a Kelvin. This is far colder than the cosmic microwave background temperature, so early black holes actually absorb more energy from the background radiation than they emit through Hawking radiation. They grow very slightly. But the cosmic microwave background continues cooling as the universe expands. Eventually, around 10 to the power of 20 years after the Big Bang or so, the background temperature drops below the Hawking temperature of stellar mass black holes. At that point, the black holes begin net evaporation, losing more mass through Hawking radiation than they gain from absorbing background radiation. The evaporation is slow at first. A solar mass black hole loses only about 10 to the power of 28 kilograms per second through Hawking radiation. At this rate, it would take 10 to the power of 67 years to evaporate completely. But as the black hole loses mass, its Hawking temperature increases, and it evaporates faster. The process becomes a runaway in the final stages, with the black hole heating up and evaporating explosively in its last moments. By 10 to the power of 70 years after the Big Bang, all stellar mass black holes have evaporated. What was once a galaxy containing billions of stellar mass black holes has become a nearly empty void containing only one remaining object, the supermassive black hole at the former galactic center. This central black hole continues its slow evaporation, radiating energy at a rate far too slow to detect, even if there were anything nearby to detect it. The Hawking temperature of a 100 million solar mass black hole is about 10 to the power of 17 Kelvin, billions of times colder than the cosmic microwave background will ever be. The black hole is essentially in perfect isolation, alone in an expanding universe, slowly converting its mass into thermal radiation over timescales approaching a googol years. The evaporation continues for 10 to the power of 98 years. The black hole's mass decreases infinitesimally slowly at first, losing perhaps 10 to the power of 35 kilograms per second, less than the mass of a single proton per century. But given the immense timescales available, even this negligible rate eventually depletes the black hole's mass. As the black hole shrinks, its Hawking temperature increases. By the time it's down to 1 million solar masses, perhaps 10 to the power of 95 years into its evaporation, the process has accelerated noticeably. When it reaches 1,000 solar masses, maybe 10 to the power of 97 years after it began evaporating, the Hawking temperature has risen to the point where the black hole glows faintly in the infrared. In the final years of its existence, when the black hole has shrunk to only a few solar masses, the evaporation becomes rapid. The Hawking temperature rises to millions of Kelvin. The black hole emits visible light, ultraviolet, X-rays, gamma rays. in its last seconds, when the mass has decreased to kilograms or grams, the black hole explodes in a burst of high-energy radiation, converting its remaining mass to energy in accordance with E equals mc squared, and then there is nothing. The last significant gravitationally bound structure in what was once Milkomeda has evaporated into radiation. The galaxy, the merger, the billions of years of stellar evolution, the trillions of stars that once burned hydrogen, all of it has been reduced to a diffuse sea of photons and particles spreading through an exponentially expanding universe. What remains at 10 to the power of 100 years after the Big Bang? A universe expanded to unimaginable size, its contents spread so thin that the average density approaches zero. The cosmic microwave background has cooled to temperatures measured in 10 to the power of minus hundreds of Kelvin, essentially indistinguishable from absolute zero. The particles from proton decay and black hole evaporation have been redshifted by expansion to wavelengths measured in light years. Nothing remains that could be called structure. No galaxies, no stars, no planets, no atoms, no black holes. Just an incredibly dilute soup of particles and radiation, spreading through a space that continues expanding forever, approaching, but never quite reaching perfect emptiness. This is heat death. The universe has reached a state of maximum entropy, perfect equilibrium, where no gradients of any kind exist, no temperature differences, no density variations, no chemical potentials, nothing that could drive any process or computation or life. The universe continues expanding forever, carrying the remnants of its former contents to ever greater distances, cooling toward absolute zero, approaching but never quite achieving perfect vacuum. Time continues passing, though nothing happens to mark its passage. The universe exists in a state that will persist for eternity, unchanging, empty, silent. Word count 100 or 500. And somewhere in that infinite expanse, in that unimaginable future, the particles that once made up the Milky Way and Andromeda continue their journey. The atoms that once formed stars, the photons released by stellar fusion billions of years ago, the neutrinos that pass through matter without interaction, all of them spreading, diluting, redshifting toward wavelengths measured in the size of the observable universe. Those particles carry no memory of where they came from. No information survives about the galaxies they once belonged to, the stars they once formed, the planets they once built. The universe's expansion has erased all such information, redshifting it into undetectability, stretching it across distances so vast that no observation could ever recover it. The story of Milkomeda ends not with a bang but with a whimper, a slow fade into silence that takes longer than the mind can comprehend. The galaxies died violently, yes, in collision and merger and starburst. But that violence was brief, a momentary flash of light in darkness. The true death takes trillions upon trillions of years, a patient dissolution where structure slowly gives way to disorder and order is forgotten. There is a strange peace in this ending. The universe will expand forever. The particles will drift forever. Time will pass forever, but nothing will change. No catastrophes remain to fear. No collisions threaten. No deaths remain to die. Everything has already happened. All that remains is the infinite settling, the eternal cooling, the slow approach to perfect stillness. And in that stillness, if such a concept has meaning in a universe without observers, there is a kind of rest. The galaxies lived, they evolved, they collided, they merged, they died. And in dying, they wrote a chapter in cosmic history that will be remembered by no one, recorded in no archive, meaningful to nothing. But it happened. The Milky Way existed. Andromeda existed. You exist. Reading these words in a brief moment of cosmic time, when stars still burn and galaxies still shine, and the universe has not yet faded to darkness. And when the darkness comes, as it must, as physics demands, as entropy requires, it will take everything: the galaxies, the stars, the atoms, even the memory that any of it existed. But for now, in this moment, in this brief window between cosmic dawn and eternal night, the universe is alive, galaxies collide, stars are born, planets form, life emerges, consciousness arises to contemplate its own existence and wonder at the vastness that contains it. This is the gift of the stelliferous era. This is the treasure of galactic collision, not the violence, not the death, but the complexity it creates, the beauty it generates, the brief flowering of order in an ocean of entropy. The Milky Way and Andromeda will die. Milkomeda will be born and will die in turn. The universe will fade to darkness and silence. But none of that diminishes the magnificence of what exists now, in this cosmic instant, when galaxies dance and stars burn and the universe is young enough to contain wonder. So when you look up at the night sky and see the band of the Milky Way stretching overhead, remember, you're seeing a galaxy in its prime, alive and evolving, billions of years before the collision that will end it. You're seeing light from stars that will witness that collision, that will be scattered through Milkomeda, that will burn for trillions of years after humanity's gone. And when you spot Andromeda, that faint blur in the northern sky, remember, you're seeing the galaxy that will kill ours, the cosmic predator approaching at 110 kilometers per second, inevitable and unstoppable. In 4 billion years, it will fill the sky. In 7 billion years, it will no longer exist as a separate galaxy. But tonight, it's just a faint smudge, a distant neighbour, a galaxy going about its business unaware of the appointment with destiny it will keep. This is the cosmic catastrophe protocol: death through collision, rebirth through merger. And finally, the long fade into darkness that awaits all structures in an expanding universe. It's not just the fate of the Milky Way and Andromeda. It's the fate of every galaxy, every star, every atom in the cosmos. The universe is dying, slowly, inexorably, following laws that care nothing for life or meaning, or the billions of years of evolution that created creatures capable of understanding their own doom. But it's also living, right now, in this moment, creating complexity and beauty and structure from the raw material of hydrogen and time. And that might be enough. That might be the point, not to last forever, for nothing lasts forever, but to exist, however briefly, however improbably, however doomed, to burn brightly for a cosmic instant before the darkness claims everything. The galaxies will die. Long live the galaxies. For as long as they shine, they light the universe. And when they fade, they'll have earned their rest, having written their stories in starlight across the face of cosmic time. Sleep now. Let the galaxies turn overhead. Let the stars burn their hydrogen in peaceful fusion. Let the universe expand in quiet darkness. There's nothing to fear in the night sky, just the slow, patient unfolding of physics, playing out over timescales that make human concerns invisible. The galaxies know what they're doing. They've been doing it for billions of years, and they'll continue doing it long after we're gone. The collision will happen when it happens. The merger will complete when it completes, and the long, slow fade will continue until entropy wins and darkness covers everything. But that's tomorrow. Billions of years of tomorrow. Tonight, the stars still shine. The Milky Way still stretches overhead. And somewhere in that band of light, on a small blue planet orbiting an average star in an unremarkable part of the galaxy, someone is looking up and wondering what it all means. It means this: you exist. The universe exists. Galaxies collide and stars are born and entropy increases and heat death approaches. But here, now, in this moment, there is light, and light is enough. Sleep well.